So so are we now following this schedule, or it's just up to me? Hello, hello.
Yeah, for the time we are following the schedule, but you can continue with your
Yeah.
time.
So okay, if it's up to me, then we'll just go ahead. Um, um, there's one thing here before we see what symmetry is and how we can use symmetry in your case. I think we need to set some ground rules here. So I will be asking questions, and and then I expect you to answer the questions. Yeah, otherwise we will not be proceeding forward. So that's the ground rule. So is I'm not going to ask you, is that okay for everybody? But I will just enforce you to say okay. Okay. Um, so I'll be asking questions throughout the sessions, and then you will then have to answer those questions, because I'm not going to show you only like how to use symmetry, because how to use symmetry you can just Google it. Yeah, you can just go to the symmetry file, and then there are many examples I will show you later in a moment. There are many files that you can just like use and then adjust to your own cases. Um, but those are more on yeah, how to use like a calculator, for example. Just press button here and there, and then you can get your answer. But then the main question is in this business is that what to do, right? So what do you want to do, and then how to do that. So that's basically and then where we get the information to do what we want to do. So that's basically what is then more important, rather than only like how do you call it, following blindly what I'm doing. Yeah, so I need to have your participations and interactive. I think if I open Symmetry, have you all opened the Symmetry? Yeah, let me know if let me know, or give thumbs up, and then or just unmute yourself. Yeah, and then say that you have open Symmetry. Then I know. Then we can move forward. Otherwise, then okay. And then before we begin with this, I think I've shared with Shahira and Winnie about we have in 2019 we have made this because I think now I don't know, because nowadays Petronas is using Symmetry, so it's their official that is their official process simulation software. Obviously among other software. So icon here was the old name of this Symmetry. So icon has a sibling called VMG Sim, and then this company VMG is bought by Schlumberger, and then they rename it to Symmetry. But then the whole stuff is the same. So in this module, we have put together some principal chemical engineering, fluid mechanics, heat transfer, thermodynamics, separation process, and so on and so forth, until safety valves, and then so on and so forth. So this is the first draft. This was the first draft in 2019. So I think you know Dr. Hadi. So Hadi, he is now the custodian of this Symmetry. So he must have maybe he has already the updated version of this module. Yeah, so it's 190 pages, so you can just go scroll through it, and then just follow this step by step. It looks different because this was icon, but I mean in principle it is the same. In principle it is the same. Yeah, go through this. I'll share it again. I've shared this with Winnie and Shahira. Maybe then they can then share this along with the other with you all. Hope. So so if you have open Symmetry, and then you can then click create new case, for example. And as always, when we create new case, that means like in your mass and energy balance class. So you need to know the components that you are dealing with, and then you need to know the thermodynamic model, so to say. Yeah. So the thermodynamic model. So this thermodynamic model is that the one that you learn in I think it's in chemical thermodynamics 2. Chemical thermodynamics 2. You learn some of these thermodynamic models. So when we click, sorry, when we click that new, and then if you accidentally close this, and then you can then click this again, thermo. You can click this thermo again, and then this window will appear, and then you can in here you can then change select the thermodynamic models in this case, or select the compounds. Yeah, select thermodynamic models and select the compounds. So I think you shared with me this integrated design project. So I don't think we're going to be able to complete this in half a day, but we'll see. Yeah? We'll see. So let's go through this. So methanol is this to produce this, and then the methanol is 95% purity. So you need to produce, see, you need to produce 95% purity of methanol. Yeah. So I think you can make a note on here. So and then you can make a note here, and then observe what I'm doing. Yeah, observe what I'm doing, and then please pay close attention to that. So in the end, you will need to have 95% purity of methanol, and this methanol is then produced by yeah, in steam reforming process. And then this steam reforming process, I think all of you is then know that this steam reforming is then going to produce syngas. Yeah, and then the methane is supplied from pipeline to fed into reforming reactor. So we have reforming reactor. So we have a methane. One of these is then methane, and then under excess steam. So we have methane. Maybe S1 is going to be methane, and then S2 is then the steam. And then in this reforming reactor, we will then have to model these two reactions. So in the end, we'll get hydrogen, CO, and CO2. Okay. Now, and then the produced syngas is then cooled down. So we have down the syngas produced over here. So in this reactor, it's then running these two reactions, and then in the end, it will then produce syngas, and it will then be cooled down to remove 95% of the excess water. So this is then the excess water. We need to remove 95% of the excess water. So there are some like 5% of water coming out. Yeah. So if we say there are like what if we assume that 100% water coming in, 95% will then be dropped, yeah, to remove 95% of excess, right? Because 100% here is then the excess of water. Um, so we will do this step by step. Yeah. So now my first question to you, because in running this reaction, you need to know the operating conditions. So what is then the operating conditions of this reactor? What is then the pressure and temperature? Yeah. Three, no, 3, 6, and 10. No, what is 3, 6, and 10? Yeah, anybody? Like I said, if you don't have the answer, then we cannot move forward. Because yeah, okay. Now find the answer, and then you can just Google that or open your book, whatever. So Um, these are all gases. Sorry. These are all gases. These are all gases, light gases, and then in symmetry they are. Let's put the components first. Yeah, let's put the components. So we need to have methane, water, CO, CO2, hydrogen. So it's this four, and then we need to have methanol, because in the end methanol is then going to be produced here. So we have. I'll put this aside to my other screen. We have so we need to go to the compounds first, and then here you can just type it. Yeah, you can just type it. C1 is then methane. So when you type C1, this list is then everything that has to do with C1. This is then C10, so C10. So this is then methane. So you can either click this, and then it's there, it's added there, or you could also do, like, for example, water, and then you can then enter once, it will be selected, and then enter the second time, you get this you get the component in. And then you could also do multiple components all together. So we have methane, water, we have then now CO, right, carbon monoxide, and then you do like a semicolon. So it means this CO is then captured already, and then hydrogen, and then you can do another semicolon. See, now you have captured CO and hydrogen, and then we need to have a CO2, right? And then we need to have methanol. No, methanol. Yeah. So now you have captured four, and then press enter, and then enter once more. Okay. Right, and then in all of these other reactions, we have the CO, we have done CO, hydrogen, methanol, water, it's there. So all of these components are in our system already. Yeah? So methane, water, CO, hydrogen, CO2, methanol. So you could also rearrange it, put hydrogen below CO2. So how we do that is then we go by sort, we click sort, and then we need to just drop this down, move down, and then we have it the same as in this trim table here, for example, and then apply sort order. Okay, now um, can you follow? Can you follow? Yes or no? Again, like I said, yeah, I need to have okay, now thermodynamic models. um, we could make various different. We could use various different thermodynamic models. Yeah. So for example, we can use thermodynamic model, one model for this block, another model for that block, and another model for that block. So you can have like I don't know, as many thermodynamic models as you can, because you know in this specific unit operations there is only one thermodynamic model that fits the best. So you could do that, or we can just lump them all together like normal people do. They just use one thermodynamic model. Hopefully, again, yeah, they will just use one thermodynamic model. Hopefully, they will then capture. It can capture the entire vapor liquid equilibrium or the entire thermodynamic properties, because all of these they are working at different operating pressure and temperature. So what we do is that we could use this advanced Spang Robinson. By default, if you click all thermodynamic models, it's all there. So it's all there. So there are many. It's just based on alphabetical order. And then if you go to natural gas processing, you get APR for natural gas by default. So you have like a short list of thermodynamic model. You go to refinery, and then you can have another shorter list. So and so on and so forth. So you could go also to go to gasification. So in this gasification, there is also this gasification 2010, but I'm not really sure if you have this thermodynamic model in it. Thermodynamic model in it. This one I don't know. So because since we are not using, because this gasification model, it's using rigorous Gibbs data. Using rigorous Gibbs data, that means we don't know what the reaction is. So we can use this model. It will then try to use this Gibbs free energy to calculate what the product components, how much they are. But in our case, since we know already, so this is then the only two reactions that we allow, and then depending on the conversions or whatnot, we can then play around with here. Yeah. So in this case, we could use yeah, we could use simple. Or let's just try this. Yeah. See if this because sometimes we don't have license for all of these thermodynamic model. I don't know if you have the license, yeah, because your license is different than mine. So let's see. So if I click done, if there is no error, that means I can use this. But if there is error, that means I cannot use this. So I click done. See, I don't receive any error. That means I can use that thermodynamic model. So now, can you when you click that done, do you see any problem? Do you see any error? And can you follow? Hello? You can just type in, yeah. If you are too shy, you can just type in. You can just put like a thumb error, error. So that means you don't have the thermodynamic model. So that means we have to just have to change it. We have to change it to a different one. go to thermodynamic model and then just use the ones that is for sure they have it or you have it, which is that's this. So this advanced Peng Robinson is not the original Peng Robinson. So BMG already how do you call it, adjust this so that it fits for natural gas refinery and petrochemical. So you can click that and then click done. Yeah. One more thing, and I hope there is no error, but if there is, let me know. Yeah. So if you go to help, you go to symmetry manual. Yeah, you go to help symmetry manual, and then here it will then open this window. Sorry, this web page. So this is basically in your program files, VMG, symmetry, documentation, symmetry, and then user manual. Yeah, it is there. It is in your computer. So it is there, and then you can just type in. So for example, if you'd like to know this advanced validation, this obviously in the equations of state. Yeah. C Evans Frank Robinson. So it gives like a short explanation on what it is. So the details of this you can go better to their reference over here. So it has all the characteristics of original Peng Robinson, but then it used this liquid phase density estimation from Penelux, and then the Matthias, and then the etc. etc. So it's not, there's no reference over here, but you can just try to Google it. Yeah? Okay, so that's how you can get to the help file, and then you can also if you want to do for example, yeah, I want to use like a reactor, for example, PFR, and then you can just type in, and then it is there. So you have this PFR example one, acetone pyrolysis, for example. So it has these things that you can follow step by step. Yeah, things you can follow step by step. Okay, things you can follow step by step. So I'll leave this to you. Yeah, so you know already how to access this page, and you know how to utilize it. So that should be okay. So I hope that should be okay. If not, then ask me questions. Yeah, you need to ask me questions, because if you don't ask me questions, I don't know what you know. So if I don't know what you know, I will assume that you know everything that I know. Yeah. So if you don't ask me questions, I repeat, if you don't ask me questions, I don't know what you know. And if I don't know what you know, I will then assume that you know what I know. Okay. Okay. So now we are here. So we have again. I will show you. We have specified the thermodynamic model, the advanced Wenger-Benson, and then we have specified the six components. Yeah. Up until here, this is the only thing that you need to know. There are many things behind this, but I think we will let it to the advanced user later on. Now we need to do so now we need to create stream. Yeah, we need to create two streams. One is then methane. The other one is then the water. So what we need to do is sorry, hold wrong. This symmetry, it works with Visio, and I think you're all familiar with Visio. So it's just like a drag and drop, simple like HYSYS as well, because the very people who developed HYSYS back in 80s, these are the same people who became the advisor of developing this symmetry. So if you know HYSYS already, you know how to use symmetry. But I don't know how well you know either HYSYS or symmetry. Nonetheless, just like a drag and drop, I can just click and then drag and drop. Yeah, drag and drop, and then can double click on this. So you can for example, yeah, I don't like to S1, so I just use then the methane string. So you can have like a methane feed. You can just rename it to whatever you want. So methane feed, and then so what is then the conditions? Okay, before we go to the conditions, you see these units. Use unit. I don't like these units. We typically use SI. In this unit set, you can change it. Yeah, you can change it. So it's very easy. Just go to SI, for example, and then click yes, and then you get it. So it has to be now in SI units. So degree C, kilopascal, kilomole per hour, kilogram per hour, and then the cubic per hour. Um, so now, before we go to that, yeah, it says here natural gas is supplied from pipeline, and then we have steam as well, and then these two, when they come to this reforming reactor, the conditions of these two streams, they have to be already at the conditions required by the reforming reactor. Yeah, I repeat, these two streams, when they get into this reforming reactor, their conditions have to be at the same conditions required by the reforming reactor. And hence, if it says that it is supplied by a pipeline, that means it's like a typical ambient temperature, and I don't know what the pressure is, could be like 50, 60 bar or something. And then the steam as well, if it's like we could like have a high pressure steam, like 40 bars or so, 300 degrees C or something. And then when it gets to this reforming reactor, which you should know, and then which you will tell me now, we need to be able to do something with this in such a way that these two conditions of these two streams, they meet the reforming reactor's conditions. Okay, now write down in the chat, yeah, if what the operating conditions of this steam reforming is. So now we assume this methane feed is coming from a pipeline, right? So that means it's ambient temperature, I don't know, 25, 30 degrees C, and then pressure. Let's make it like I don't know, 50 bars or something. So if it's 50 bar, while our unit is kilopascal, and this would be like 50 bars, we can just easily type 50, and then before you press enter, yeah, type 50 and then press space instead of enter, press space, and then you will get this units. So all of these units are available in Symmetry, which you can then select. So you said that 50 bar, so that means this is 50, and then select bar. And then when you select 50 bars, it will then automatically convert it into kilopascal. Yeah, 50 bars is 50, 100 or 5,000 kilopascal. 1 bar is 100. Right? And then we can just say what is that? We know what the temperature and pressure is, but we don't know. We haven't specified what's in it. Yeah, what's in it is only methane. So that means we go to the mole fractions or the mass fractions. Up to you. You can use either way. So take the mole fractions because it is on the top part. So type 1, and then this new window pop up, and then you can just either press enter and then click OK. Yeah, when you click OK, and then one is then methane and the rest is then 0. And then it knows because this only methane, this stream only consists of methane. That means at this temperature and pressure, this methane is in the vapor fractions. Yeah, is in the vapor fractions. Uh, um, I will explain to you what it means by vapor fraction. So vapor fraction means it is in vapor basically. If it's 0, that means it is then in liquid. Yeah, and then the rest I will tell you along the way. It is strongly related to the your phase diagram. So if you go to phase diagram, for example, yeah, just take a phase diagram of water to make it easy for you to understand. Because see, um, yeah, I don't know what happens. We go to image, very slow. Okay, now tell me what is then the operating conditions of this um, what was it again? The reforming reactor. Go on. If you because if you don't know, that means we cannot continue. Because if you don't know, that means we don't know what to put into the reactor. Yeah. So go back to this. If you see this, come on. You know what happens. Um, what happens with my internet? Um, Anyhow, if you can see this, um, so so this is then the phase diagram of water typically, and then this is our triple point. This is then the critical point, and then this is this part is then solid. This part is then the vapor. This part is then liquid. This part is then liquid. Sorry, this solid. This is a liquid. This is vapor. How do I know? Because temperature is on here on the x-axis. Yeah, typically I see this temperature is on the y. But nowadays, temperature is on the x-axis and then pressure on the y-axis. We can just say so at one atmospheric. This is then the 0 degree C. So below the 0 degree C, which is on this area, below this the 0 degree C, it is solid ice. Yeah, you know that by heart. So it's solid ice. So this is then the solid part of the region, and then you increase the temperature, it melts, and then increase the temperature until it reaches 100 degrees C, and it will then boil. So this part is then the vapor fraction. Sorry, the vapor fraction is equals to zero, equals to 1. So if we say that vapor pressure is equals to 1, that means this in this area, and then vapor pressure equals to 0, that means it is in this area. Yeah. Okay, and then typically this kind of process simulation software, they don't have the solid part information, so we don't have it. Um, and we could also do what you could also do, for example, yeah. Instead of specifying this, okay, I will do that later on. But then up until here, I think I hope that you understand this vapor fraction concept. Temperature is 30 degrees C, pressure is 50 bar. So if I do this, yeah, if I do this, if I would like to know, for example, where's that graph again? So at this pressure, at 50 bar, for example, at 50 bar, somewhere here, at 50 bar, what is then the corresponding temperature on this line? This line from here to there, this line is what we call like a saturated a vapor and liquid, because there's only one component. So this is then the saturated line, saturated line, differentiating between the vapor part and then the liquid part. So this saturated line, because we know this saturated line as a data, so at a certain pressure, for example, this 1 bar, the saturated line is then 100 degrees C, but at 2 bars, for example, it will be like a 110 or something, and so on and so forth. So if it's a 50 bar, what is then the corresponding temperature? So to do that, we need to specify either uh, is the component saturated vapor or saturated liquid. So the way to do that in symmetry is that yeah, you remove this. We need to know at 50 bars what is then the temperature, what is then the saturated temperature. Yeah. So if this methane is in the saturated vapor, that means the corresponding temperature is then the saturated temperature. That means this has to be keyed in as 1. So it doesn't have the data. So it's either something's happening in the flash calculation. So it doesn't have any data on the saturated vapor of 150 bar. But if it's water, you know it. If it's then if it's liquid, can we do liquids? So it means if it's liquid, that means the vapor fraction equals to 0. If we press enter, it's also there is nothing. It's also there is nothing. So we will do this exercise again in water so that you understand. So in this case, we can just say 30 bar, and then since we don't know, yeah, what is that document again? We don't know how much is then coming in, and then it doesn't say here how much is then the methanol that you need to produce. Okay, so it's something for you then to figure out. So in this case, we can just simply, I don't know, maybe 1 ton an hour, so 1,000 kilogram per hour. So when everything is filled in, you can see this remark as solved. That means it can then calculate the molar flow rate, volumetric flow rate, and so on and so forth. We can click this drop down. So you have this energy, enthalpy, entropy. It's all in relative. Yeah? In relative, it has this baseline of temperature for enthalpy and entropy behind this ISIS, behind this symmetry. Molecular mass, 16, density at this temperature and pressure, and so on and so forth. So compressibility and so on and so forth. Yeah. So it is there. So it's green salt, and then you can see that this is then the light blue. So in my version of symmetry, light blue is vapor. And then now we make another one, steam. Do you have any questions so far? If any questions, can you follow? Is there any questions? Can you follow? And then what is then the operating conditions of the what is then the operating conditions of the reformer? Nobody knows. If nobody knows, then I don't know what to say. This then now the steam, yeah, steam. So we can just say steam feed or feed steam. You can just put your name as long as you can recall later on. So steam feed. So what do we say on this steam? Because I don't know what is needed, so we'll just assume something. Yeah. So 300 degrees C. And then in this case I can play around, yeah, because this is steam. So steam, that means we put one in water, and then we'll see. So now one in water, if you say that it's 1 atm, right? So 1 atm is, that means 101 or if you can just put one and then space atm like this, enter that one. So it corresponds to this guy. And then we want to say, okay, what is then the temperature, the saturated temperature at 1 bar? So the way to do that is that I think you have learned this, yeah? You have learned this in chemical thermodynamic 1. So vapor fraction is equals to 1. That means it is on the dew point, yeah? Vapor fraction is 1. That means it's on the dew point. So you know dew point, bubble point. So bubble point is about to boil. So that's a saturated liquid. Dew point is that about to condense. That is then the vapor fraction equals to 1. So you put the here. So if I put 1, that means it knows already, and that the corresponding temperature, the corresponding saturated temperature is 100 degrees C. Things that we know. But if this is then, I want to have like a bubble point, which is then the vapor fraction is equals to 0. It's about to boil. It's about to boil. But it's still in liquid. We can just also press enter, and then the corresponding saturated temperature is also 100. Why 100? Because we have only like one component. In this case, it's water. One component. If you have more than one component, you will have a different bubble point and the dew point. So if I Google again, so I'm now showing you how to learn from Google, because I think this is one of the most important skill nowadays. So now, if you have, for example, if you have two components, I don't know what the components here, but it has component 1 and component 2, and 0 is 0 in component 1, that means 1 in component 2, which is this, and then the half component 1 means half component 2, 1 component 1 means 100% component 1, it's, you must have the corresponding 0 component 2. As you increase the temperature, because it has two different components or more, in this case 2, you have, this is then the bubble point curve. So these are all of this. For example, take this 50%. So we have 50% component 1, 50% component 2. When you increase the temperature, it goes up until it reaches this point. So at this point, this liquid is about to boil. It's about to boil. So that's what they call its bubble point. It's about to boil. So this is then the corresponding bubble point curve for every compositions of the component 1 and component 2, basically. So it starts to boil, and then it boils. So you have the higher you go in temperature. So the higher you go in temperature, the more vapor you build. The more vapor you build, and in the end, there is no vapor left. There is more liquid left. There is no liquid left. So at this point in time, it's all saturated vapor. Saturated vapor. If you drop the temperature a little bit, you will get liquid. Yeah, it's about, so that means also it's about to dew. It's about to condense. It's about to condense as well. So because if you drop the temperature a little bit, it will then condense. But if you increase the temperature more, yeah, so this is then saturated dew point or saturated vapor or dew point curve. If you increase the temperature more, you will get to the superheated region. Okay, so that's what it means. So in between, for example, in here, so from here to there, you take the middle part. So this middle part is then 50% vapor. 50% vapor. So in this 50% vapor, you can see what is then the corresponding temperature, what is then the corresponding component 1 in liquid, what is then the corresponding component 1 in vapor. Yeah? I hope you know. If not, then you have to go to your chemical thermodynamics one. Or we can just have another session on thermodynamics. Yeah, it's also fine. I'll tell you everything. Now, so now I showed you. Now we go back to business. So let's assume that this is then the, for example, this is then the 40 bars. Yeah. I don't know. 40 bars. Just pick some numbers because I've seen this in one of the plants more than 10 years ago. So 40 bar, you can just press space and then bar and then enter. So at 40 bar, it's about to boil at 250 degrees C, 249 something. So at 40 bar, this water is about to boil at 249 degrees C. But if it will also boil at the same temperature basically. So this 249.7 is then the saturated temperature. So if I don't want to see this, I want to have it like a superheated. That means I can go to 300 degrees C or 250 degrees C even. So if I delete this, and then I know already the saturated temperature. So if I go to 300 degrees C, so at 300 degrees C, it is obviously at the superheated conditions. Obviously, the vapor fraction is 1, yeah, as you understand this already, hopefully by now. Okay, now before we move further, I will just you can with symmetry you can then key in. You can then keep the window on top, just anchor that over there. So you have the steam feed and then you have the methane feed. You can also keep it on top. Let's see. Now with this assumption, 1 ton an hour, you have 60 kilomole per hour of methane. And then if you go to the reactor, sorry, to the reaction, so we have methane, 1 mole methane, 1 mole water, and then another mole of water used to react with the CO. So that means, and then we don't know what the conversion really is. Yeah, this is something that you have to figure out. And then in this case, if we assume because syngas is then CO and hydrogen, um, and then we can then assume, okay, I don't know, so if I have this one and then I have this also like one, it means I don't have any water left. So this water has to be more than 1, but how much more is something that we don't know at this point in time, something that we don't know. That extra amount will be separated over here. So but for simplistic case, if this is then 1 mole, we can just assume that this to be like 2 mole, yeah, for a current for the starting point. So that means this is then the 62. That means I can safely put here like I don't know, 120 for example, or 150. Let's put 150 kilomole an hour. So I have that 150 kilomole an hour. It's a 2,700 kilogram an hour. Okay. Now, and then we can just save this. Make sure you save always. You save always this. Yeah. Save it by any name you like. I save it as methanol from steam methane reforming, so that I know what's in it. Is there any question? It's 40 minutes. Yeah, I've been talking for 40 minutes already, so I will stop here. Is there any questions? Hello, hello. Can you follow? Is it too fast? See, how do I know whether I am too fast or too slow? Whether you understand it or not? If you don't make any noise. No questions. Okay, very good. You have to be more interactive. Yeah, you have to let. I mean, you have to. I mean, the kids nowadays, right? They can express themselves better in TikTok, in Twitter, in the Instagram or whatnot, and then you have to be able. You have to be able to translate that expressions of yourself into classroom, right? Into a workplace environment. Because if you stay quiet, people do whatever they like on you. Yeah. um, Okay, now if you don't have any questions, so now I'm questioning you. What is then the operating conditions of the reactor? Because that reactor, because this feed, it needs to be conditioned in such a way so that it can fulfill the reactor conditions. So what is then the operating conditions of that reformer? Come on, I'm wait. I give you like 2 minutes. Yeah, I give you 2 minutes. What is then the pressure temperature of that reformer? You can scroll down, yeah, to see whatever that Symmetry has in the library, and then you can go to reactors because this is then the reactor. So we go to reactors. Since you don't have the gasification stuff, so it means we need to have another workaround. So we're not going to use the gasification. Where is that gasification? It's not here. So we can either use equilibrium reactions or equilibrium reactions or the compression reactions. Yeah. Because this gives energy. It's in the equilibrium reactions. So you could also find out gasification if you have only like plasma gasifications and stuff. Equilibrium reactor. Can Google equilibrium reactor. Equilibrium reactor controlled by thermodynamic equilibrium. Yeah, thermodynamic equilibrium. And then it's also have this Gibbs reactor stuff there. So in this reactor, we don't specify the reactions, but we just specify the how to call it, the components, what's component that are possible coming out of the reactor. So it will then use this Gibbs energy minimization calculations to calculate the product. So in this case, it's always about this reformer, because this reformer typically works at higher temperature and lower pressure. It's very close to ideal then, and then it gets to the equilibrium already. Yum, 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 yum. Okay. Hey, where is then the reformer operating conditions? Come on. Yeah, well, if you don't have it, you can just sit here until 12 o'clock. Because I don't know that information and you don't know that information, so what do we do? Right? What is then the operating conditions of the reactor? Because if you don't know, that means we cannot move forward. One way. Hello. So steam methane reformer. Steam methane reformer. Very easy, yeah. I don't know why. What happens with you? Nah, 20 bar, 250, 360 degrees C. So how do you get that? Yeah, how do you get that? Um, so if I Google this,
Search online.
yeah, you search online. So which online reference that are you using? Very good, yeah. You search online. That is one, at least one step. Even though that's not a good step, it's one step. You search online, which is very it's a quick, how do you call it? It's a quick search. Um, um, how do you, because in Google, I mean, in all of this online, there's not everything is correct. Yeah, not everything is correct. So you need to find out what are reliable sources. Number one, reliable sources are textbooks, especially textbooks in the old days. Textbook in the old days, they are reviewed and reviewed and reviewed and refined so that they have stood the test of time. But nowadays, you can go to like this energy.gov. It's a US website, and Science Direct is also like a scientific publisher. So you can use this one and that one as your two sources of information. Wikipedia is also like a good one to start. It's not something that you can base your argument on this, but it's just a good to start. So the way I typically do this, I just if I don't know anything, yeah, just search online and then see the publisher. So this then a well known. I can just open one, and it's also a publisher. And then the Wikipedia. So three to five is basically okay. So I'm not going to go to the next pages. Yeah, it's enough already. Just to have a quick information. So if I go here, Wikipedia says see it's equilibrium reactions, yeah. This steam methane is equilibrium reactions. You can see the energy and then the uh, steam methane the this one. See, large amount of heat needs to be added. Um, Lies in the range of hundreds of temperature. Yeah, it's much higher than what you specified. That's why I asked how did you get that number. Yeah, good, that one. Yeah, it's about in this range of temperature. It's 700 to 1000. It's close to 1000. So you can see it here, there. Yeah, it's somewhere here and then somewhere there. So somewhere here and there. So these are then the typical operating conditions depending on the technology and then the product that you would like to have, because different operating conditions they will then give, because it's equilibrium, yeah, so to say. So it can give different or various compositions. So you can go through here and then read. Yeah, you have to read. You have to read. There's no other way other than reading. You have to read. Um so let's use this. Let's use this. So it's about, let's use somewhere in between 800 and then 20 bar. So let's stick to that. So 820 bar. So that means because these all two are gases, and then the different pressure. These are 50 bars. The methane is 50 bars. We need only 20 bars, right? And this one also 40 bars. We need to have 20 bars. So both of our streams they are already somehow higher than what is required in the plant. Yeah. So if that is then the case, that means we have to reduce the pressure. So how to reduce the pressure? Typically, we simply destroy the energy by expanding it through a valve. Typically, yeah. You can later on you can Google what is the better way to do that. So if it's a to valve, just drag and then drag another one here, and then double click on that. Okay, so now you can just because it goes to methane feed, yeah, click this drop down list and then you can have this methane feed out, yeah, methane feed out. So I need to explain to you what is then out mean before we go to that. So in symmetry you can also find it here, yeah, a port. I think port is somewhere here. Symmetry fundamentals. Port. Yeah, somewhere here. You can just Google this. You can just search for this later. Fundamental concept port. So you can read this later on. But I'll just quickly tell you. Um, okay. Where's that thingy? If you click drop down here, methane for out, methane dot out. That means this streams, this methane dot out is somewhere here at the end, because it does the calculations and it will then send the results of the calculations at this output, and this part is then the import. This then import, and then this then the output. Yeah, so that's why this part of the unit it has the import over here, and it is then the output. So the input of the valve has to be connected to the output of something else. So in this case, methane feed. So it's there. So we have see in and out. So in is over here, out is over there. So in is then over here. So we just need to reduce the pressure, right? So you could do many ways, yeah. Number one is then you can do that. You can just because 50 to 20, that means you have to reduce by 30 bar. So you could use 30 over here, or you can just simply put 20 there, and then let Symmetry calculate that for you. So 20 bar, so a bar, and then there. So 20 bar, the delta P is 30 bars, and then the CV is 1.88. So that means this valve is a very small valve. The opening is 100%. You can just also make like a 50%, just for the sake of playing. So 50%, that means you will then have to double the size of your CV basically. Okay, so let's keep it like 100%. So it's a full valve opening, and then it expands, so it reduces the temperature for this methane, for this methane. So you need to read more on the Joule-Thomson effect to understand why some gases they reduce the temperature and the other gases they increase the temperature. Okay, so and then the same we can go to the other guy. Steam feed out, and then also a 20 bar bar. So drops temperature by 2 degrees, and then we need to have what stream coming out on the other side. So here you can just type in steam to reformer. You can just type in there, and then this is automatically um, uh, assigned, because the conditions is already there. It's just that the name is not in yet. So for example, the same goes here. The conditions is there, but just the name is not there, because this unit is not connected to any stream. So you can either drag and drop, rename it, and then that's another hassle. So we can just easily write this down. Methane to reform. Okay. Any questions so far? Yeah, because this is Visio. So you can zoom in, control, and then scroll up, zoom out, control, and scroll down, and then to the left, shift up, shift left, shift right, shift left, shift right, control up, control down. So something like that. So it's easy. So you can also if I want to extend this, just like Visio, control. You can see control. See? Control, and then you go to the right, and then you can see that, then you can just drag, so then you have a bigger full sheet. Valve and relief valve. Relief valve is also a valve, but it is named so relief valve because it has another function. It has only one function basically. So this relief valve is then only to relieve what's in it. So for example, you have um, I'll show you how the easiest way to learn, so that you can do this on your own later on if you don't know. Again, googling skill is the best skill and the most important skill nowadays. So relief valve, valve. So you go to image. This is then the relief valve, but I want to see a relief valve attached to a vessel, so that I can show you. This one. So if you can see this, so this is a vessel. See this vessel, we have liquid and then we have vapor. So this vapor obviously pressurize this vessel, this tank or vessel or whatnot. So and then obviously this vessel is designed at a certain pressure. For example, it is designed at to withhold the pressure of like 10 bar, for example. And then if something happens, you have too much of vapor, or if this liquid is vaporized, I mean the pressure here is increases to more than 10 bar. So say for example, typically it's 5 bar, and the temperature increases, it vaporizes, the pressure goes up 6, 7, 8, 10. It reaches the design pressure of this. So in order for this tank not to explode, so these vapor that 10 bar vapor that has to be relieved somewhere, so that's then the use of this relief valve is to relieve whatever vapor contained in this vessel. So if we say if the pressure here is 10, the design pressure is 10 bar, and then we want to protect this vessel, yeah, we want to protect this vessel, obviously we have to relieve it to a pressure, at a pressure lower than 10 bar, because at 10 bar this vessel breaks. At 10 bar this vessel breaks. So we need to relieve this at 9.5 bar, for example. So the set pressure of this relief valve is 9.5 bar. So when the pressure here increases from 5, 6, 7, 8, 9, 9.1, 9.2, 9.3, 9.4, 9.5, this valve will open. So when this valve opens, it relieves whatever that is coming in. Either it relieves to the atmosphere, like in this case, or it relieves to a flare, or it relieves to a scrubber or whatnot. So it will then release at 9.5 bar. So when it reaches 9.5 bar, the vapor here goes up, and then the pressure, obviously, because the vapor goes up, and then it reduces. Yeah, the pressure reduces. There's no more gas, or gas is then reduced. So the pressure drops to 9.5 to 9 and 8 and so on and so forth. Yeah, so this is then the relief valve. But a simple valve is just to open and close. You have a pump, you have open. You have a bathroom you have a bathroom, right? In your bathroom, you have a valve, right? The water tap, you have a valve. So that valve is a valve. The valve in your definition. So it's a typical valve. There's a valve that we are using here. This valve. It's not the relief valve. It's just to regulate the flow. Right? You regulate the flow, or you regulate the pressure. That's this valve. Okay. Any other questions? No. We need to have it in the in 100 in 1000 degrees here. So or maybe 800. I don't know. 800, 900. Just pick a number. So 20 bar over here. So we can just say we can just hover our mouse to this. It's 20 bar. Right, so you can see 278 degrees C, 20 bar. But if it's too much of a hassle, you can just double click on this and then put this, because this information is important for you. So you can just add to click here, click on the stream, and then right click, and then add to PFD. Right click, add to PFD datasheet. So it is there. So we can just zoom in a little bit. So steam to reform pressure is 20 kilopascal. The same goes with this guy. So we need to know the pressure, this pressure here, because this is important for you. There. Okay. So because you want, or someone he wants to have like a bar, I want to have 20 bar. Why are you showing me 2000 kilopascal? So just right click here, right click, and then config PFD datasheet. Right click and then config, and then yeah, hopefully it will appear. It'll take some time in my case, but I don't know why. Yeah, yeah. So in the meantime, while waiting, okay. So you can just change the unit to bar, for example, bar. Okay, and then the format you can just say I don't want to have decimals, I want to have like a 0, so no more decimals. And then to apply, that means if you click update, this one is will be updated only, but if you apply it, this will be applied as well. So apply to all material streams. So you can see 20 bar, 20 bar. And then we mix it and then we heat it. Yeah, it's easier than we heat them all separately. Mix it, so mixer, and then you can also do it this way, and then you can also do it that way to make it easy. So when you connect it, you can see that this is already like a dark, so it means it is solved already. Solved already, and then the 20 bar, 20 bar, 20 bar. So lowest P outlet is then the calculation, the default calculation mode. So if 20, 20 coming in, outlet should be 20. So if it is 40, 20, that means the outlet should be 20. Yeah, it has to it accommodates the lowest pressure in the inlet, and because otherwise it won't flow. So feed mixed feed. Rename it accordingly so that you understand. Um, okay. Okay. So now the you see the color changes here. I don't know what happened, so we'll just get into this. Um, Now we are mixing. See, pure vapor of steam, right? Steam, and then view pure vapor of methane here, and then when we mix them, one goes at 278 degrees C, very high temperature. The other one goes to 16 degrees C, very low temperature. So when we mix them, obviously the mixing temperature should be somewhere in between, which is 193, because of this very cold vapor. Some of the steam will have to condense, like for example this. So vapor fractions is no longer one or no longer pure vapor. We have 0.00203 water. Sorry, liquid. Yeah. So we have some amount of liquid, um, and then so this is then the compositions of the water and methane in this fixed stream. So because it has now, or it has a different vapor fraction compositions, the color now changes to a darker blue. Yeah, you don't have to memorize the color, but it is there so that I explain you so that you understand. And then we heat that to 900 degrees C, right? And then you can just, you can just um, um, drop down, and then feed to reactor, right? To reformer, feed to reformer. Now, in this in this heat exchanger or heater or whatever you want to call it, the goal of this unit, is to increase the temperature. Yeah, the goal of this unit is then to reduce the pressure, and the goal of this unit is then to increase the temperature. The goal of this unit is to mix the streams. So since the goal of this unit is to increase the temperature, that means we need to know what the required temperature is. So what is then the outlet temperature? So you can do in a way, so many ways. You can do you can add a delta temperature. So this plus a number plus this number, you will get that one. Or you can just type in what your number here or there. So in this case, if we type in the 900 degrees C, um, so means the delta T is then 700 degrees C. Yeah? And then it doesn't converge. I mean, it's not solved automatically because it still needs the pressure balance. So the energy balance is there. So we have the energy. The mass flow rate is the same. Yeah. But then the volumetric flow rate is not there because we don't know what the pressure is. And since we don't know what the pressure is, we need to specify the pressure or the pressure drop. So in this case, if you specify the pressure to be like for example, 50 kilopascal or half a bar is a typical number, or 30 kilopascal or zero point 0.3 bar is a typical number. Put the half a bar, for example, 50 kilopascal is then the delta P. So that means your outlet pressure is 190, sorry, 1950, which is lower than what you want to have, right? It's lower than what you want to have. And this pressure, it needs to enter this 20. Yeah, you have made your mind at the inlet of the reformer, it needs to be 20. If you say that 19.5 is fine, and then it's fine. But if you say, oh, I don't want to have 19.5, I want to have 90. That means you have to increase the outlet pressure here. That means you have to increase the outlet pressure here. So since these two are very important, let's see, can I do this? Yeah. So I can add to PFD, and then this one also add to PFD, and then yeah, this two is important at least for the time being. So this then that. So we have fulfilled our 900 degrees C, but we haven't fulfilled our 20 bar. Yeah, you could say, well, I have fulfilled my 20 bar. It's also up to you. But I'm now showing you what happens if you don't want to have 19.5. So that means I have to increase this. So you could also do this, yeah. That means if you know that you are losing 50 kilopascal over here, that means you have to increase this by 50 kilopascal. So 2050. So if you increase it 2050, this is 2050. You can can click config here because it's I can put 0.0 and update. And then because this works on the lowest pressure, so it will then take out this pressure. So we have to increase this pressure as well. 2050. So now you will get your 20 bar over here in this bit to reform. Okay, so save. Now you got to go to the first reactor. So it's already 1 hour, and then you can only manage up until here. Now, any questions before? I haven't drank my coffee and it's already cold, so I need to make a new one. Any questions so far?
Hello.
Yes.
Hello, sir.
Yeah.
Hello, can you hear me?
Yeah.
I want to ask how to add to the PFD because just now I tried to click on my site, I didn't find the option. Can you show me once more?
PFD, this one. This is the PFD.
Later, I think the video is not.
Sorry. Maybe it's better that you share your screen. Then I know. Share your screen.
Share my screen.
You know how to share your screen?
Yeah. I need some time. Or maybe sir, you show me one time. I try to see my screen first.
So this then if I click this, I will then stop sharing, and then you can then see on the same exactly on the same spot. You can then share. That's how you share your screen. Because I'm not really clear on your questions because this is flow sheet. Yeah, this is flow sheet. Right, like in the VCO. Do you see this?
Later, sorry. How to share?
Do you have this flow sheet?
Yes, I have this flow sheet.
Okay. So
I'm trying to share my screen first. Which one?
You can just share your screen.
Sir, can you see my screen now?
Yeah. Very good. 1 minute. It disappears. It's gone.
Now cannot.
No. It's gone. It's black. I don't know about the others.
Oh, like this and now.
1 minute. Now it's good. Now it's good. Okay.
Okay.
Okay. So what's the question?
You look good, how to show the pressure, those things, because I try to click, right, don't have.
Double click first. Double click. And then here you can then right click.
Right click.
Right click. For example, you go to you highlight the temperature or pressure or whatnot. Then right click and then add to PFD datasheet. Yeah.
I see. Because previously I'm using the S1, right, and then S1 can show all the properties, so I'm actually figuring how to add on Symmetry also.
Yeah. That's how we do it. But I don't know. I think there should be if you okay. Now you can go to config. You have this 20 bar, right? You right click on that. And then go to config, and then in this configuration you can add whatever you want. So it's a P. Okay, I will show you my screen. It's easier. So that's how we do this. A minute. So for example, I want to have this this one, and then configuration.
I cannot see your screen yet.
Sorry. I thought I've shared my screen. No.
Okay. I can see now. Now can.
Okay. Very good. So in this case, you could do I think there is a way, but I don't know. Yeah. But what the way that I know, yeah. You can have this the out, yeah. So you can go to out, and then you can show also as well the yeah, just highlight this, and you can see so mass flow, for example, and then you can put it on the right, and then maybe you want to see the mass flows of each component. For example, we have methane, and then you could press control, and then hydrogen, hydrogen, water, yeah, mass flows, and then what methane and water, and then you press this, and then you get all this, and then you can then configure the units, for example, this can be bar, this one in kilogram, and then if this is in kilogram, I don't want to have any decimal points, no decimal points, something like that. And then pressure, I want to have only like one, um, there, and then update data sheet, and you have everything. I think you can also rename this display name. So by default it takes out this, but if you don't want to see this out stuff, why do I want to see this? I don't want to see that. For example, yeah. Methane, and then the water, and then update, and you get this, and then save. Don't forget to save always. Okay.
Okay. Thank you, sir.
You're welcome. Very good, yeah. Very good. So we need people like you more. You need to ask
Sir,
questions.
so you cannot see my screen already right now.
I can see your screen. Yeah, I saw your screen.
You still saw my screen.
No, this is my screen.
Oh, okay.
Yeah. Okay.
Because I didn't stop sharing just now. I'm just wondering whether
No, if
I
someone
will stop.
no, you don't need to stop. If someone shares his or her screen, and the previous one will be overlapped, or will be how do you call it, replaced.
You'll be close.
Okay, now fit to reformer. So we know that we have fulfilled the required conditions for temperature and pressure, and then now we go to the reactor. Since we don't know, we're not using any of these fancy reactors. Yeah, we simply use a conversion reactor. Okay. Um, or we could do. I think we will just try both. Yeah, try both equilibrium and then conversion. So we'll see what the difference is. And then equilibrium. Um, so you can take there, and then you can then rename this. Rename this as reformer. Can then conversions, please. Yeah, you can do so that you understand. And then the delta P, yeah, typically we have to specify the delta P as we specify delta P for the heater, yeah? Because it's all about mass and energy balance. So delta P in this case is just put typical number, 30 kilopascal or 50 kilopascal, for example, half a bar, um, and then we need to specify the reactions because this is conversion based. So specify the reactions. Go to reactions, and then here we can click add or edit. So this one, so you can name it, yeah, reaction one, for example, reaction one, and then the base component. So in this case, so you see, so you can see methane is then reacting with water. So in this case, it is more, I think, more appropriate to use methane as a base component. That means we will then do the calculation based on methane, not on water. And then in the second reactions, we will do the calculations based on the CO, not on water. This water will be left hanging, so it will be calculated accordingly. Yeah, so methane as a base component for this first reactions, and then CO will be the base component for the second reaction. So in this case, um, so we can see base component is then methane. Now the reaction, I think you know already if you know how to use sciences. So this is going to be -1. This is -1. This is 1. This is +3. Yeah, -1, -1, +1, +3 from the stoichiometry. So methane is -1. So I just type in -1. Water is -1 as well, and then carbon monoxide is 1. You can also see while I'm typing here, you can see the balance in moles. So it has to be, this has to be 0, otherwise something is wrong. So it's 1. So that means I need to have is -6, yeah, -6, and then we know that hydrogen is 2. So 2 times 3 is 0. 2 times 3 is 6. So 6 minus 6 is 0. So this hydrogen is 3, yeah. See, 3 hydrogen. So 3. And then it's 0, so it means it's the balance is it's already more balanced. And then the conversions, we can you can specify anything you want. So in this case, for example, I don't know, 99.9 conversions into percentage. This is in percentage, yeah. That means if you put 99%, that means 99. It's not 0.99. 99.9, for example. Okay. And then the reactions number two, base components, then CO, and then this is then CO is the -1, see, -1. You can see that this is then the molecular mass of CO, yeah, 28. And then the water is -1 as well. And then this is then the CO2. CO2 is 1, and then the hydrogen is 1. There, see. And in this case, we can say we want to make use of all methane, so that's why I put this 99.9%. So there should be like some methane left over or something. And then the CO, because we need to make we need to have more CO. So we could, like, I don't know, maybe 10% or 20% CO is then being reacted over here. So it's something that you need to find in the literature. What is then the typical steam methane reforming outlet here? So that means just put a number. So that means this is then like a 20% or something, and then click OK. Okay, and then the summary. In this case, we need to know the pressure. We have defined the pressure. We have defined the pressure. There is a 50 kilopascal pressure drop, and then we need to know different. We need to different because this conversion based, yeah, this we do whatever we like here. We can how to call it? We need to declare. Sorry, we need to declare this reactor. Is this a kind of like an isothermic reactor or adiabatic reactor? Yeah, if it's isothermic, that means the inlet, the temperature stays constant throughout the reactor, or the temperature, or it's adiabatic. That means there is no energy coming in and out of the system. Yeah. Again, I repeat, so we need to make sure, we need to, sorry, not to make sure, we need to define or declare whether this reactor, is it operating in adiabatic manner, that means no energy coming in or out of the reactor, or is this reactor is behaving in isothermic way, that means the temperature is kept constant throughout throughout the reactor. So how to know this? Typically, we can see this. Yeah, we can see this. I think it's mentioned over here. So these reactions is like an endothermic. So large amount is needed to keep the constant temperature. So we could use like a constant temperature. In this case, that means we need to have it in isothermic conditions. So in that sense, if it's isothermic conditions, we need to make sure that the temperature stays as it is, or like if you want to keep it like 900, if you want to keep it like a 950 or 1000 and so on and so forth, so it doesn't matter. So it's up to you. And then the amount of energy needed to keep this temperature as it is, or at for example, yesterday, for example, at 900, we want to keep it like a constant 900. So the amount of energy needed to keep this temperature at 900 degrees C, it will be calculated in this out Q. So for example, in this case, I press 900, and then I have this amount of energy. This amount of energy, see, 3.8 megawatt, 3811. So 3.8 megawatt is needed to keep this temperature constant at 900 degrees C. Or if you say this is adiabatic, yeah, if this is adiabatic, that means no energy is then going out and in. It means that the energy is zero. And then we can see, because this is highly endothermic, it says over here, it's highly endothermic. See, um, so we have, this is then one reaction. So it's positive, it's endothermic, so it needs this amount of energy. And then we have the second reaction is somewhere here. It is compared to this one, this 200, this is only 40, so this is only less than 1/5. It's about 1/5. So endothermic is then controlling the system, yeah. So hence we see this very low temperature. So very low temperature. So we don't want to have that. That means we are not doing anything physically. So we want to keep it like 900 or 100, 900 something. So 900. So we need to supply this amount of energy. We need to supply this amount of energy. Okay. So in this case, this is then the outlet reactor. So we can sorry, I can just rename this here. Reformer outlet. Voila, something like that. Okay. Any questions so far at this point? Any question?
Sir,
Yeah.
can I ask, like, how can we add like like material, like if I forgot certain
If you
material
forgot, okay, very
in
good, very
my
good, very good.
work
If
in my how yeah, if I forgot something, how can I
fine,
add
fine,
that?
fine, fine, fine. No worry, no worry. So if you got to add, or maybe we need to add more flow sheets or whatnot, you can go back to thermo, go back to thermo, and then in the compound you can just add whatever. So for example, nitrogen. Yeah, I know in my case it's I don't know. It's not needed anyhow, but it's if it's there, so I can just enter, and then you can see nitrogen is new. So you can add. So in my case, I don't want to have this, so I can just delete this. Okay. So is that answering your questions? Is that clear?
Yes,
Okay. Okay. Yeah,
yes,
just
sir. Thank
go
you.
to just go to this thermo. Anything if you want to change temperature, if you want to change thermodynamic model or compounds, you can just go back to this thermo, and then you can see it's when you click this, the solver is inactive. That means you can do whatever you want. It is not being calculated. So if its solver is active, it means it's calculated automatically. It's calculated automatically. Okay, okay. Let me see here. Now this is one, yeah, this is one. I for me typically, yeah, because it's already like too much, and then I would like to have like a more like like a control panel or a user interface. So a good way here, it has this spreadsheet or process calculator. We call it process calculator. So we can have this process calculator as like a yeah operating window, so to say, user interface. So we can see like a user interface. It will become handy. I'm showing you because as you can see, for example, you put, these are all inputs, yeah, the one that you put in bold, this bold are all input, yeah, this bold are all input. So we have inputs in the valve, we have inputs in the feed, we have inputs in the feed, and we also have inputs in all of these unit operations. So we have inputs in the outlet temperature, pressure, drop, and then these conversions. So you can see, for example, yeah, later on, if I want to vary the amount of methane and steam. So that means I can just put like feed input. I can just bold and then underscore, and then you can see. So that means flow rate. Yeah, I want to vary, for example, flow rate only. So methane, and then this is then steam. So in this case, I go to methane. I go to methane. Yeah, once I type them all, so I need to have the input over here on the right. So because I want to vary, yeah, I want to vary the flow rate, for example. So I vary this flow rate because this is input. So I highlight this, and then right click, and then I go to copy connections. Yeah, copy connections. It is not copy whole table. It is not copy. It is not copy path. It is copy connections. Yeah, copy connections. So I click this, and I put next to this. Right click. Yeah, put next to this. Right click, and then paste connection. Paste connection. You can see methane underscore feed. So methane underscore feed is this guy. Methane underscore feed, and then dot in. Dot in means because this is at the inlet. This is at the inlet. And then dot mass flow because we are copying the mass flow. Yeah, so this should be the right information. So if I copy that, it's 1000. So it's the visual is ugly, I know, but okay. And then we know that this is 10 kilogram an hour, right? Kilogram an hour. And I need to know, because we calculate the steam in terms of mole balance, right, of the methane roughly. So I need to know how much is then the mole balance. So I can also copy this. So this one I delete. I put steam over here. This is then also methane. This is then in mole balance. I can just highlight this mole balance, mole flow rate, and then right click, and then copy connections. Yeah, right click, copy connections again, and then paste connection. Copy and paste connections. Copy and paste connections. So I have this now. Kilomole per hour. And then I think I've seen something like a mole ratio, something somewhere. Mole ratio. No, no mole ratio. How did I see mole ratio somewhere? Anyhow, so you could also make like a mole ratio, yeah. So mole ratio, for example, 2. So that means if you pick 2, that means the steam flow rate should be 2 times. For example, this is more like an Excel. So 2 times this guy. So this is then the steam flow rate. So kilomole per hour. So in that sense, or maybe 2.5, for example, 165. So that means we have this bold means this bold again. This bold is something that you key in. Yeah, this is our input, like this one. This bold, the same bold is something that you input. But if this is not bold like this, 62 and 62, it's something that is being calculated. Again, yeah, bold something that is input. Not bold is something that is being calculated. So in that case, this is also our input, but this is the input already in only in process calculator, so it doesn't have this bold. But if you want to make it consistent, you can just click Control B and then it's bold, so that you know in the end later on, yeah, next week or tomorrow. And then the steam, I need to have the steam. So this steam, we use this as an input, right? We use this as an input, 150. But in our case, if you put the mole ratio of 2.5, it has to be like 155. So in that sense, we can then right click here, copy connections, yeah. Right click, copy connections, and then paste here, paste connections. Yeah, highlight this and then paste connections there. So you have 155. So this 155 over here, it is no longer an input in this sheet. So in this window, but it is an input somewhere here, which is controlled by this guy. Okay. So by doing so, you see that we have two connections here. We have two connections. One connections to this methane, and another connections to this steam. So this connection to the methane, and this connection to the steam. So you have that's why we have two green lines. But later on, it will get messy. So I typically hide PFD connections. So there's no green line. Yeah, I typically hide this. See, I hide this. Okay, I put this aside so that because we need to know this up until here, right, before we move on to this user interface. Do you have any questions? No questions. Huh? No questions. Okay. And then we have another one, also a very important one. Yeah.
Hello.
Yeah.
Can you show me where to find the user interface, because I tried to type, but
This process
I
calculator.
didn't find it.
Process calculator.
Process car.
Process
Oh,
car.
I see. So the function of it is for us to easily visualize what data that we need to validate.
Yeah. So you don't have to, for example, you don't have to click this. You don't have to click this and then change it. You can just simply change it over here. So pay attention here. This is that 1000 of methane, right? Methane 1000. So if I change it to 1200, you can see this 1200 automatically change. So I don't have to go to this.
Oh, okay, understand.
Yeah, it's much more like easier, so you don't have to click every of these unit operations because not all of them are important, and then sometimes we also get confused where did I put here somewhere. So another important one as well, we know that this temperature is also important, so we could also say okay, reformer input. So in this case, reformer input is obviously the temperature temperature into the reformer, which is this here. Temperature into the reformer is copy connections, and then there, and then in the reformer itself we have so in here we have the reformer conversion base. Action 1, action 2, you know 1 and 2, yeah. This is then 0 and 1, so it's 1 and 2 because 0 and 1 is it's based on Python. This is in the fractions, which is then from 0 to 1, but we know this is then the 99.9%, yeah. So this is we copy connections, put it there. This is also copy connections, and then put it there. So so that's it. Save, and then you get up until here. Up until here, these are the important inputs that we can play around. Okay. And then we'll try, as I promised, that we'll try another type of reactor, the equilibrium reactor. See what happens. So this equilibrium reactor, so it will use the same input. Sorry, it will use the same stream, yeah, same input basically, same input. So how to do that? So this is then the power of this symmetry. This can be easily done if you click on this, open this stream. So how to do this? We can just easily click create port. So we create port. That means we create port from here. So we click create port. So what do you want to copy? So we want to copy the outlet, the inlet, the outlet, or any other properties. So if we copy the in and out, it's basically the same. If we copy that, typically it's out. It will then copy the whole information. Yeah. If we copy only the signal port, it will then ask us which port, either temperature or pressure or mole or whatever. Yeah. But in our case, we are going to use the whole stream we will use the whole stream that goes into the reformer into the what is this, the equilibrium reactor. So we can just copy. Yeah, I will repeat this again. create port, and then copy, clone, copy the string. So we have out, we have in is over here, and then out is over there, and then out one is somewhere here in between here. So how to know that? This one is quite a bit tricky. So you close this, so we can just keep it open, and then we double click because there is out dash one stream coming from here. We just don't see it. So the way to do that is double click here, and then it has to enter here. So we can just drop down. You can see out fit to reformer, which is this fit to reformer, and then out dash one, which is this guy. See, so it's coming from the stream into the reform, into the equilibrium reactor. So we could reform equilibrium. Again, delta P is we keep it like a 50, and then temperature is also okay, now it's a bit trickier just to make things as the same. So this cell, we are going to use the same temperature, yeah, same temperature here, constant, the same temperature there, constant. But this cell, it is connected to this temperature. Sorry, it's not connected to that temperature. It's not connected anywhere else. Basically, there's a input temperature. So temperature of conversions, so you know, yeah. So this is then this guy, copy. Oh, I cannot copy this. See, I cannot copy this. So the only way to get that here, it's not copied. I can just use this in the reformer outlet. Instead of keying the temperature here, I can just key the same temperature there, yeah, at the outlet. So I will just delete this and then put the temperature here. So this guy is taken from that, and that one we can copy easily. Can you follow? So instead of specifying the temperature in this reactor, like in here, like it was, I specify now the temperature outlet to be on the stream itself, this reformer outlet. I specify it here. So this one I can connect it to the control panel. This one I cannot connect it to the control panel. So hence this is the trick. Is that can you follow? This one is more like a trick, yeah. It's nothing. There's no fancy thing. Yeah. So now, since the temperature of conversion is over here, it is connected to there. So I need to make a temp reformer equilibrium. Temperature equilibrium. So in this case, we are going to use the same temperature. Let's use this. Enter. And then again, I don't think we can just copy paste this. Copy. We cannot paste this, yeah, because there's something there. So what we could do is then reformer outlet. Equilibrium. So we can then instead we use the same trick. We copy this, copy connections. We put it there. Paste connections. Yeah. Okay. So both of these reactor, they're using the same temperature. So why I do this is just to show you. And then now the reactions, we can just edit or copy from. Let's see if we can copy from. This one is the only reactor. Select all, and then okay. So I have these two reactor, equilibrium, and then this one is also a constant. This is something that we need to have, which apparently we don't have it, unfortunately. I forgot that we need to have this. So we need to make a table of temperature and then experimental K. Yeah, so it's more like because equilibrium depends on the temperature, so we need to have the data on the temperature and the equilibrium itself. If not, then we don't know, and then it will not know. So in this case, yeah, we cannot proceed with this equilibrium. Gibbs, if we say Gibbs, we can do so because it will then only doing, like I said, this Gibbs free energy minimizations. So because we have specified the composition, the outlet. See, we have specified the non-reactive compounds. Non-reactive compounds means whatever is being reactive is then methane, water, CO, hydrogen, CO2. Yeah, this is not reactive. But because of this Gibbs free energy minimizations, this methanol is not included already because it's not being the lowest in energy of from the Gibbs free energy. Nonetheless, if you encounter reactions, say for example, I want to exclude CO from the reactions or methanol from the reactions, you can just take this, and then it will give you the corresponding conditions. So now, with this Gibbs free energy, go up at 900 degrees C at the same operating conditions, we can then we can then compare, yeah, we can then compare the Gibbs free energy calculations with the one that we assume, because here we assume reaction conversions. So these two we assume for this reformer, but this one we just use the temperature and then we allow this Gibbs free energy calculations to calculate for us the outlet composition is. And from this perspective, since we don't know what this conversion is, we don't have the data for that, I would tend to base our assumptions or the calculations on the Gibbs free energy, because in the end it's at higher temperature, 900 1000 degrees C, and then the this Gibbs free energy situation is applicable in that sense. So how to compare? So now I want to compare. Let's put this comparison. Put the unit always here. Put unit always. Because we will forget. Reformer output. We want to compare only the components. We have I don't know if I can copy. No, I cannot copy. We have methane. We have water, CO, hydrogen, CO2. Right? Yeah. And then want to see let's compare the kilogram an hour, yeah. Conversion reactor out, and then Gibbs equilibrium reactor out. So we can see how to do that. Simple. Again, I don't think we can copy. No, not copy connections. We can only copy it from the stream. So we copy it from the stream. Okay, this one. Conversion first. So this one is conversions. We copy the mass. So methane. Copy connections there. Water. Copy connections over there. CO. Hydrogen, and then CO2. Okay. Now the same goes with the with this guy. Copy methane, and then water, and then CO, and then hydrogen. This is a bit yeah. So now save. Don't forget to save. We can see apart from methane, one is then one is then 10 times bigger. Water is about the same. CO is well slightly lower. Hydrogen is slightly lower. Is also so all in all, it's not that bad. Yeah, I mean this whole stuff is not that bad. Um, I mean these assumptions that we make in comparison with the Gibbs calculations is not that far off, except for this methane. So how to make this, how, because this is then the methane, so we can if we put the 0.999 it's 1.2, we need to have it like 100 times bigger. uh, so that means I can reduce these conversions to 99%, for example. 0.99, it's 12, or it's 90% in this case, yeah, 0.9, 120. So it's very close now, right? The same goes with the CO. The CO, we have how do you call it? The outlet of the CO in here is very high, well, relatively higher compared to the CO over there. That means this conversions is not that that low. So we need to increase it to 0.3, for example, and then you get the 1300 something. So this is then roughly the numbers that correspond to the Gibbs reactions, yeah, roughly. Or you can further fine tune this. Um, Leo, why do you want to control this? Okay. So now I'm giving you another trick, not trick, another tool as well, yeah, tool. So we will use to do this calculation automatically. So because we know the methane is in the first reaction, CO is then the second reactions. So we want to make sure that the difference between this and that is very small. So how to do that? What we just did, we do like a trial and error manually, yeah. So I want to show you how not to do that manually. Error, I can just say error is then the absolute yeah, you can just say, you can just make a square root of error, yeah. So this is then this minus that and then square root. So you have the error, the square root of error is then the 89. So I want to minimize this. So if I want to minimize this, that means if this then being minimized, that means this number will be approximately the same. And I want to know how much is then the conversions that corresponds to this minimum number. So how to do that? We use controller. We use controller. Controller. See this controller. Double click. And then this has to play around, yeah, and then you can apply the same concept in later phase or in other situations. So I want to make sure this becomes 0. So this is then our PV, or the target variable. Copy. It says PV here because in dynamic simulation you will use the same controller as well. So this is okay. Right click, copy connections, and then right click, paste connections. You get this 89. And then the target is then 0, right? Obviously, yeah, I'm going to make it 0. And then what do we manipulate? The operating variable, operating variable, basically the manipulated variable. What do we manipulate? We manipulate, like we just did, we manipulate this number. So we right click, copy connections, and then right click, paste connections. You get this. Okay. So now we are missing step value. Here you can have you can do I don't know, maybe maximum step value is then 1. I don't know, because you manipulate this um, failed. So maybe I don't know. It's something that requires some numerical knowledge. Step size fail. Yeah, maybe 1. For example, I don't know. Nah. Can convert Jacob something also I don't understand. But you could control setting more than I don't know what happens here. In this case, maybe this is too small. Uh, 1.1. I don't know what happens. Okay. I'll look into this later and then I'll update you. Yeah, I'll look into this later and I'll update you why we cannot do so. I think there's something to do with the. I'll let you know later on what I think once I get this done. But this is basically the way how we do the this adjustment or controller stuff. I don't know why it doesn't work. This one I don't know. It typically works. Mm, 0.9. Um, I don't know why. Could not convert. Yeah, I don't know. I don't understand this message. Anyhow, um, I'll put this inactive. So we'll skip this. I will let you know later on. Yeah, I'll check into this what happens. Nonetheless, we are now here at the outlet of the reformer. So we have done save. What we have done is see, it's already like close to 2 hours, and then we are only until here. Okay, we're only until here. Now this stream S3, this is then the outlet of the reactor, and then it will then be condensed to remove 95%, of the excess water. So hey, up until here, do you have any questions before we go? Any questions? No questions? Not in the chat. Any questions? Hello. Any questions? No. Well, if it's no
No
questions.
questions from me.
Huh? No questions.
No questions, sir.
Okay. It's all clear. Oh. This is cooled down, yeah. It's cooled down. It's not like a scrub or a quench. So it says cooled down here. So that means we just simply need to reduce the temperature in this particular case. So we are going to reduce the temperature from 900 to a temperature that can then condense water 95% from what is coming in. So what we can do in this case, mathematically, yeah. To be honest, I don't know how to do this practically. You can then lower this. We typically use like a quenching. but in this case no. We can just use mathematically, say we reduce this temperature, we cool it down, so we can work on this Gibbs free energy. Okay, so we have a condenser. So this condenser, basically you have it has two functions. This condenser has two functions. Number one, so I'll just show this. So it has two functions. Number one is then reduce the temperature, and then the second function is that because you reduce temperature, the vapor, the water vapor will then have to condense, right? So once it's condensed, we then have to separate that into vapor and then into liquid. So there are two functions. So the first function is then to drop the temperature, from 900 degrees C to a certain degree C, and then after that it will then separate the vapor and liquids. Yeah, so two functions. So that means in this case, I repeat, we are going to need two functions. Number one, reduce the temperature, and number two is then to separate the vapor and liquid. So from that perspective, we need to have two unit operations in this regard. Number one is then the cooler, which obviously needs we need that to reduce the temperature. So delta P is just put like 50 kilopascal. Sorry, we have to connect this first. Reformer outlet this way, and then reduce the delta P, and then the delta T, or the outlet temperature, we can just simply reduce it to just make a guess now, I don't know, 200 degrees C, for example. Yeah, 200 degrees C. And in this case, this 200 degrees C, you can see it's all still vapor, so there is no condensation whatsoever. Okay, but this is just a guess. And then the profile plot, I didn't need that. Yeah. Okay, something's happening. Okay, yeah. Uh, and then we need to have the separator. Yeah, need to have the separator. Okay, cool. Um, hmm, okay. Takes this reformer out cold. Yeah, and then the liquid water excess as liquid, and then this guy is cold vapor. Well, whatever you want to name it. Condenser out vapor. And then we see nothing. We can see so liquid is zero, all zero, and then everything is still in vapor. And then you can also see the color. You can also see the color. This is all gray. Gray means there is no flow. Yeah, gray means there is no flow. So what is coming in here, everything is still in vapor. So what we could do is that we could also make a, now this one I think we can make a calculator. 95%, yeah. 95%. So we can have because we need to have this 95%, right? Just I don't know why, but let's, for the sake of just taking it as it is. Condenser. Water in. So water in is the one that is coming from the reactor outlet, right? So this water in, is then the amount of water at in. So that number, copy connection, yeah, the outlet of the reformer, and we put it there. Okay, kilogram an hour. And then 95% in the liquid, right? In the liquid water, in liquid, it should be 95%, right? 95%. So how much is that 95%? That is then this guy times that guy. Why is this not calculating? Oh, 0.95. Somehow so somehow it doesn't take this 95%, it takes the fraction. Okay, so just use fraction. So this has to be basically in this water excess, right? This has to be in the water excess. It has to be somewhere here. So what we could do is then play around with the temperature, reduce the temperature in such a way that this is then the water. So the water excess over here. The water excess over here with that stuff is this stuff, right? This is the target. So this target has to be close to this number, yeah, close to this number. Okay. So how to do that? We use the same controller. Controller. So yeah. So this is what we want. Target. We want to have it 1700, yeah, just to make 750. And then what we can control, what we manipulate is this guy, this temperature out. Okay, step size is I don't know, 100. Error, blah blah blah. So it doesn't do anything. It tries to do something, but apparently it doesn't do anything. So if we try to how to call it, it doesn't do what we want. Yeah, that's not necessary. So if we reduce this manually to 150, it doesn't do anything. It doesn't do anything. So what can we do further? Because we don't know what the temperature is. Yeah, we don't know what this temperature is. We can use so we could do what we call, like, we could use one of the tools, which is then the case study. So this case study is more like a sensitivity analysis. We can then vary the temperature here in such a way that we monitor how much is then the water excess. So that's what we could do. So case study, we can rename this as condenser. We can this one, I think we need to make it. We need to disconnect. From anything. Sorry. So we vary the temperature. Not copy connections, but then the add to case study. See, add to case study. So we have to get this window open. Yeah, if this window is not open, if we right click here, there is no add to case study, so it has to be open. This window has to be open. Okay. Condenser. And then we add to case study condenser, and then it is then independent variable. It is independent variable because yeah, it's something that we vary. It's something that our input. So we vary that. And then the outlet is what we want to see. What we want to see is then the water excess. Yeah, so the water excess. So this one we close, water excess. So I want to see how much water in here. So we add case study as the dependent variable, yeah, because it is calculated. So we are varying this from minimum and maximum. So maximum is that 200 degrees C, yeah, because we have done that 200 degrees C. Minimum could be like, I don't know, maybe 50 degrees C or something. So how many points? 11 points, and then you can just go up. So 11 points, 50, 65, 80, and 80, and so on and so forth. So you can just change it to 10, for example. I don't know, 50. That's up to you. 20. Or you could also say, I don't want to see the points, I want to see delta 10 degrees C, for example, and as it is then 16 points. And then it says ready, so you know what you vary, which then the outer temperature here, and then you know what you monitor or what you want to know. Yeah, and then we click local. So in this case, we have a local in process means one core, or you can also run in multiple core. So obviously this will take much more effort. It will be much more faster. So up to you. This is only one how to call it, one hand, so it doesn't really matter. So it's done. So the results, we go to the results, and then we can see at 200 degrees C, no web, no water. 190 degrees C, no water. 180, no water, and so on and so forth. Until 140 degrees C, we will have some water. And then our 1700 something is somewhere around here, yeah, 60 to 70 degrees C. So we know this is our starting point. So we can also plot this, yeah. We can also plot this. Come on. See? So temperature, x-axis, water, y-axis. So we need to have 700 something degrees C. So somewhere here, So we can then use 60 or 70 degrees C. Sorry, 60 or 70 degrees C, 70 degrees C, 60 degrees C as the initial point. So you could do what you could do now. Once you know this, this then 70 degrees C, for example. So you can have now you are condensing 25%, and then we do this. Let's do this here. I'm curious why this controller is not working. Sorry. This is what we manipulate. Copy connections. Sorry, copy connections. Copy connections, right? Here. This is then now. This guy. Copy connections to that one, and we want it to be 750. 750, 1750, 1752, for example, and then we step size is 100. Yeah, it is already the error between this and that. It says the error between this and that is already like lower than this guy. If I reduce this to 5, okay. Anyhow, let's do this. 100. Yeah. So why is this not running? Yeah. This is a great result. It's not running. Can, so it's not updating. Maximum absolute error. Oh, why is this? 10. The absolute error was too much. It was 10. So now absolute error is then 1, then it goes to a very small difference. Now it's a 0.1 to make it very accurate. So now I get this. The temperature out is somewhere in between as we know it, 68 degrees C. Um, think that is so I've shown you how to use case study. I've shown you how to use controller to adjust your operating variables. Yeah, so this one works very well. And then you get your excess water over here. So let's see what is in here other than water. So we have only water and some amount of hydrogen, some amount of carbon dioxide, so mostly water. So we are now save, and then we are now here. We are now here in S5. So 2 blocks in 2 hours 11 minutes roughly. Any other questions? Do you have any questions? Can you follow? Yeah, I don't know. Yeah, I think I've spoken too fast. But since you don't make any interruptions, seems that you can follow me very well. So I highly appreciate you for that. So let me know whether you can follow me very well or not. Any questions? Or this is too much already? Or you need to have a break? Because I can work this out without any break here. Let me know. So now you need to know we are now here. Yeah, we are now here, not there. We are now here at the outlet of the condenser. So and then this syngas it needs to go to this methanol reactor. So I'm asking you now the same questions like in this reforming reactor. So what are the required operating conditions for the methanol reactor, for the methanol to be produced? So I'm giving you 2 minutes to get me that answer. In the meantime, you can also ask me anything. Hello. Hello, hello. I don't know if you were there, or I don't know if I've been speaking by myself for the last 1 hour. That one, that one I don't know. Hello, hello, hello. No? Um, uh, shall we continue this or no? Done. So reactor. This one is methanol reaction is more like a fixed bed reactor. So it's a really like a PFR type of reactor. If we have the kinetics, we can use the PFR type of reactor. But if we don't, and then we can just assume the conversions like what we have assumed before. So it depends on the information that you have. So you can either give me the operating conditions as well as the conversions if you want, or if you have it, or you have to have it, or you can also give me the operating conditions as well as the kinetics of this methanol reactions. So it's all up to you, yeah, because in the end you have to go to the field and find all of this information. Otherwise you'll get fired, huh? And you can go do something else other than the chemical engineering. Now, any questions? Hello, is there anyone else? If there is no anyone else, then we can just close this meeting. Hello, hello, hello. No?
Yes,
Okay.
sir.
Are you there, or are you sleeping, or are you doing something else? Because that is then the limitation of this online class, right? So online class, I don't know what you're doing. Um, shall we continue or no? Hello?
Maybe take 5.
Huh? Yeah?
Take 5.
What?
Maybe a
Fine.
break.
Say it again. Say it again.
A break?
Ah, a break. Okay, fine. How many minutes? I think we can have like a 10 minutes break or something.
Yeah, sure, sir.
Yeah. So
Sir.
11 26 then 11 25 26. We can go back here. So let me know, yeah, if you want to have a break because I don't need break. Save first and then you can have your break. Okay. So it's 11:25. Yeah. So we have 2 more minutes to go. I have a question here from Leo. Leo, are you there? Hello? Hello, hello. Ah, um, so if, recently come across compressors analysis from some chemical engineering blog, but not to understand and it. Okay. You can just Google it again, yeah, if you understand it. Um, compressor search. It's a bit yeah, it's not typically taught in fluid mechanics of chemical engineering department. So we discuss more on pump curve, but very rarely on the compressor curve. Compressor search. Um, the concept is very easy. Basically, you can have it, yeah, in all YouTubes. You can just go in YouTubes and then you can learn a lot from many of these experts. But I'm going to share with you just a image. Just a quick discussion on this. This one, that one, yeah. This one is easy. Can you see this? Yeah? So as in the case of I think you have seen this in the pump curve, but it's for centrifugal pump or centrifugal compressor heads. They work basically. I mean, you will see the same. Well, it's not like this, but it's roughly. So we have a volumetric flow rate that pass through the compressor, and then we have the head or delta P or pressure out or whatnot. So at the y-axis. So this is typically, so if the compressor is or the pump runs, or the compressor in this case runs at a certain speed, like 3000 rpm or 3600 rpm or whatnot. So this is then your operating point. So that means at this point you are now delivering this amount of flow rate, with this polytropic head, with this head, yeah, with this head. So this head corresponds to this flow rate. I need to compress. I need to find the block diagram so that it's easier for you as well. See, I'm very lazy to to draw things for you. This one, it's easy. Um, Bigger, how to make it big. So you have inlet of the gas, and then it typically we have typically like a knockout dram, so to remove or to knock out all the droplets. Um, so just to remove all the droplets, so it will then protect the compressor blade. So it will then compress the gas, yeah, compress the gas. So it will then compress the gas a certain amount of flow rate, and then this amount of flow rate, for example, and then the discharge pressure is this number. Okay, so if you see this, and then we have a check valve, and then we have a valve somewhere, and then if there's also like a flow control or something, so it will then if this valve is then closing, yeah, so if this valve is then closing, that means the flow through this compressor will reduce. Yeah, if this valve is closing, that means you are not exporting gas to this line, so the flow is reduced. So the flow is reduced. That means you will go to this. You will go to this line. You follow this line. So because if you go to the left, the flow is then reduced. Yeah, the flow is then reduced. But then the consequence is that you will have a higher pressure. You can see. So when it goes to the left, you will have a higher pressure. Yeah, we reduce, and then if you reduce it further, reduce it further, reduce it further, until you then have like a minimum flow. If there is no flow, so for example in this case you have this it reaches this surge line. At this very low, flow rate, at this very low flow rate, you have a very high pressure. You have very high pressure here compared to this guy. You have very high pressure here. At the very low flow rate, you have very high pressure over here. So this pressure, it can then also fall back into this compressor like a surge. Uh, to compensate for that, so in order not to go, in order that this flow rate is not this low, we need to make sure that the flow rate is always above this blue line. So they call it like anti-surge line. So this line you can draw anywhere as long as it is above the surge line. So this surge line comes from the compressor vendor. So if you draw this on this blue line, so then we need to make sure that the flow rate, it has to be always higher than this number, so if you are now operating at a very low flow rate, yeah, due to capacity reductions or whatnot, and then say for example you are now operating at this flow rate, so to prevent you from this surge from happening, you need to have additional extra flow rate over here. So this additional extra flow rate over here, yeah, it will have to go to this anti-surge valve. So this valve. So the total flow rate is this, for example, in this blue line. The total flow rate is the blue line, and then this flow rate is then the one that goes back through this anti-surge valve, and then this flow rate, the one that here from 0 until here. So this flow rate is the one that goes there. So you need to in this case you have the one that goes to the client. The one that goes to the client over here is this flow rate. This flow rate. Not very good at moving my hand. But then the additional flow rate over here from red to blue, this one is the one that goes via this anti-surge valve. So at least you with this anti-surge controller system, you protect the compressor from getting into this surge line, because at this surge line the flow rate is very small, the pressure is very high, there is a risk of going a backflow, I guess. Yeah, this one I'm not really sure, but there's something that you have to because the pressure here is very high already. Because this pressure is very high, it can also flow back to the, because the it will flow from the higher pressure to the low pressure. If this pressure is too high already, it can then flow back, and then it will then damage the compressor. Yeah, it will then damage the compressor. Flow back over here, it will then pressurize this line. Once this gets to higher pressure, it will then flow back to there, and then the gas is then pumping, and then this whole thing will then go to the right, and then since it's closing, and then you will then have a lower flow rate, and then it goes back over here. So it's when it goes over there, it moves like this. It goes to the right, and then no flow goes to the left. Higher pressure over here goes to the left, to the right again, then no flow, and it goes to the left again. So it's something like that. So the presence of this anti-surge controller and this anti-surge valve has to be taken care of. Yeah, the design of this and the sizing of this anti-surge valve has to accommodate at least we will not pass this we will not below this blue line, will not flow below this blue line. So it has to flow above the blue line basically. So above here, this valve will then be closed. Below this blue line, this valve will be open, roughly speaking. Okay. I'm not really sure if okay. So is that clear, Liu? Oh yes, we could do that in HYSYS. We could also do the same thing in Symmetry. Yeah, it's the same. As long as you can model this, you need to model this system. You need to model this system. So you have a vessel with the capacity, and then the lines with the capacity, and you have a compressor with its the performance curve. So you need to get this graph from the compressor, and then you have to have the cooler, and then you have to have this valve, and then this valve. So it's all in dynamic simulation, yeah. It's all in dynamic simulation. So I don't think we will go through that this in this half an hour. So dynamic simulation will take another 1 day in itself, because I need to explain to you what dynamic simulation is, how we can do dynamic simulations, and then with some examples, and then we go to this search. But to help you a little bit, I think we have it here. So if you go to the symmetry, you go to program files, yeah, program files, and then VMG, symmetry, and then the documentations, I guess. You have manual examples, plan examples. So plan examples, for example, you have a flare and relief system, maybe. No. Manual example, vapor storage, piping and flow, compressor. Water tank equipment. This one is, we have a compressor curve. I don't know. Maybe you can open that one. It's compressor curve, yeah. I don't think that is the correct one. You can open this. So well, anyhow, we can have another session on this if you want, yeah. But for today, we'll keep it to the because we have only like half an hour extra left, so we'll keep it today. We'll keep it today on the your on this guy, yeah. So we will do this later on. If you want, you can have another sessions on the dynamic simulations, and then this compressor surge. But the concept is the same, yeah. I mean, I'm just calling this is the only concept. So it's just a matter of modeling this. So in dynamic modeling, we need to know the capacity of each of these equipments. So we need to know the dimension, the pressure, sorry, the pressure, the length, and then the volume, diameter, length and diameter, and then the performance curve of this guy, and then also the capacity, the volume, and then also the K value for the pressure drop calculations, and then the duty. So dynamic simulation, it takes much more than the steady state, because in steady state we don't really care. That's nothing. Yeah. In steady state we don't really care on the size. Yeah, right? Like for example, in this vessel, what is then the size of this vessel? Well, we don't know, and we don't care. We don't know, and we don't care. So we will use this mass balance, inlet, liquid product, and vapor product, to size this vessel later on, and that sizing we will then use it to the dynamic simulation. So it will take another 2 step further from steady state. We make the mass balance like what we do here. That's one step, and then we size it. That's the second step. And then once we size it, we will then model that in dynamics. So it's 3 steps basically, or 2 steps from the steady state, from the mass balance. So yeah, you just have to be patient, and then it's also a good practice for you, yeah, because you said that you have the high C simulation model in dynamic, and then you can then copy that input, the same input, you copy that to the symmetry. Yeah, I will show you later on. Yeah, I'll show you later on. Yeah, um, maybe we can make, yeah, just discuss with your teammates or whatnot, and then we can have another separate session on that. It's also possible. Yeah, just let me know. From now on, we need to continue and then stop at 12. Like I said in the beginning, we were not going to be able to complete this, because because you don't have the information. So every time I ask you the questions, you cannot answer me. You're gonna give me the answer. So now my questions to you again. So um, for a few times already. So what are the operating conditions for this methanol reactor? Because without knowing this, just like in the reformer, yeah, without knowing this, we are stuck here. Yeah, excellent, Zahran. So it's a methanol reactor. So it needs to be like around this number, 250 degrees C and then 100 bar something. And this is then the one that goes to that reactor. Yeah. So we have now 68 degrees C, and then we have how much in pressure? We have only like 19 bar, right? 19 bar. So what to do? Yeah. So that means we have to increase the temperature, and then we also increase the pressure, right? We have to increase the temperature, we have to increase the pressure. But which one to do first? Zahra and others, which one to do first? Shall we increase the temperature first, or shall we increase the pressure first? What to do? So I'm asking you all of these questions again because process simulation is just much more than just clicking and keying the information. So it's not about that. So all this clicking, drag and drop, you can just Google it. But the most important part is to understand the process. So temperature, you need to increase the temperature first. Why is that so? Let's do to get you understanding, because if I only say this to you, it won't get to your head. So let's do it your way. So number one, we increase the temperature, and then we increase the pressure, and then we compress it. Yeah, that's what we do. And then the second one, we do it the other way around. So we increase the pressure, we increase the temperature, and then we compress it. So that's what we do. So we'll have like two alternatives, just like in this case. So the same way, when you design a process, you have like a alternative. So we'll do it your way so that you can see it yourself. Obviously, because we are going to have two alternatives, we need to copy this stream. Yeah, we need to create a pod and then clone it. So I have now two, this out and then another out. So now let's do it your way. We increase the temperature first. So we increase the temperature to yeah, make it 250 degrees C. Condenser out, the first one. Make it to 250 degrees C. And then delta P is 50 kilopascal. So you have this, yeah, 250 degrees C and stuff. And then we compress it. So this is then the condenser. Whatever you want. Fit to methanol. One. Yeah. Okay. Now we increase the temperature and then we increase the pressure. Increase the pressure is compressor. Fit to methanol one. And then to reactor. Fit methanol. Methanol reactor, particular. So outlet pressure is, how much is that? Just take 100 bar. Yeah? Bar. 100 bar, and then just assume polytropic efficiency of, I don't know, 80% or something, 0.8. Yeah. Okay, yeah. I'll put this here so that you can understand. I'll put this here so you can understand. You can, when I show you this, you already know what is wrong with your option. But and then I put this the other path. I put here because this compressor is that compressor. Yeah. Put 2 PFT data sheet and then temperature. Then you know, yeah. Okay. Now the second option is then to increase the pressure first. Go here, and then the feed methanol 2. We feed the same information, 100 bar, right? Yeah, bar, and then the 0.8. So it's basically the same, and then cool it down. Hey, need to copy this. This duty, and then the outlet temperature. Okay, and then we have feed to methanol 2 out, yeah, and then delta P 50. This is our temperature to 250. Huh. Okay. Okay. This one I put outlet temperature here. Oh, this is not. Okay, I'll show you. Yeah, so I think you know this already, but so the first option is then to the first option is already to increase the temperature from 250. Sorry, from 60 to from 60 to 250, and then from this 250 we increase the pressure to 100 bar. So in doing so, we end up with 8,000 degrees C, 8,400 degrees C of outlet temperature over here, which is practically not possible. And having this 250 degrees C into the compressor, it will also damage. I mean, we don't have any seal that can withstand this 250 degrees C of temperature. So what we have is only like typically 150 degrees C. So we limit the temperature across the compressor to about 150 degrees C. Yeah, so if it goes above 150 degrees C, we'll have to reduce the outlet pressure. We have to reduce the pressure, the pressurizing system. So the same applies in this case. So in this case, we compress it first to 100 bar, which is in this case it goes to 8,200. So instead of 8,400, because it starts from 250, it starts from 60 degrees C, and then it ends up like 8,400. So having one stage of compressor like this is also a problematic, because we will not be able to withstand this temperature higher than the start temperature of the sun. And then having this high temperature is also not a good one. So because of mechanical problem, yeah, because of mechanical problem, as well as because if we increase the temperature, so it starts from 250 degrees C until 100 bar. So the duty is for something something to the power of 8. But in this case, it starts at 60 degrees C, and then we also compress it to 100 bar, and then the duty is 3.6 something something to the power of 8 watt. So it saves about 0.4. It's about 0.4 something. It's about 10% or more. So it saves about 10% or more energy. So that's also another situation where if we want to compress, we typically compress it from a lower temperature. So if it's higher temperature, we either have to reduce it a little bit. One is then to avoid this mechanical failure of the seal, and then number two is then to save some energy. Yeah, because at a higher temperature, imagine, yeah, because we are now compressing gas. So this gas, if it's at higher temperature, that means it's moving around. It's moving around, and then you want to contain it and then to compress it. So it takes much more power of you. So for example, if you have small kids, you have like small siblings, or small nephews or niece. So you want to put them sit together. if they are a kind of people like calm people, and it's very easy for you to tell them to sit down and watch TV and do something useful. But if these kids, they are very energetic, yeah, you put them sugar and they're very energetic, it's very difficult for you to contain them, right? To tell them to grab them one by one and then tell them to sit in the sofa or something. It's going to be very you need much more effort and energy to do so. So the same analogy is applied here. But in this case, we will, so that means we will have to use this. We have to compress it first and then cool it down later on. But in this case, we cannot do also in one step, yeah, in one step, because it will end up at 1,200 something. So this then compressor 2, sorry. So compressor 1 is a no-go. So this option is what we need to do. Okay. You can see the pressure ratio is 5. So from 1900 to 10,000, it's a compressor 5. We typically use a compressor ratio of less than 5 or 1 point something until 2. So pay attention to this temperature. If it's below 150, we stop. If it's not, we keep increasing. Yeah. So if we compress it from 1900 to 2500, I failed to calculate diabetic efficiency. Okay, I don't know what happened. Yeah. We're compressing it from 1900 to 200. Let's do the other way around. Is it percentage or? Oh, I'm confused with this percentage now. So, so it's not point, I guess. Yeah, now we are making mistake, or at least I'm making mistake. So it's a percentage. So it's not 80%. It's 0.8%. So if I put 80%, so it's more likely it's 80%. So it's 80%. Okay. So I was wrong. So again, instead of so let's redo let's redo the story. 100 bar, yeah. See, from 250 you compress it to 10,100 bar. It requires about 1 million watts. But from 60 to 100 bar, it requires about 0.6 million watts. So you save energy. That's number one. And number two is that again we need to be able to get this temperature into the compressor lower than 150 degrees C because of mechanical reason. So we need to get this temperature down to less than 150. 2500. You can increase it further. The pressure ratio is 1.3. You can increase it to 1.5, for example. So 3000. 3000 seems okay. 3500. 2500 is also okay. So you could stop here. It's lower than 150 degrees C. At least you can. So now in this case, because we have compressed it to to 35 bars, from 19 bar to 35 bars, and then the temperature goes to 149 degrees C. So we need to cool it down to typically we will use air cooler. So that means we will have to cool it down to or cooling water, for example. So we cool it down to about typically 50-60 degrees C. So in this case, because we've done so. So this cooler C2, cooler. So we reduce it to from 149, we reduce it to 60 degrees C. So 60 degrees C, right? And then we cool it, and then we compress it again. So this is then what we call like a methanol compressor, syngas compressor, first stage. Syngas first stage cooler, so that you know. Okay, and then you can copy, copy, and then the paste there, right? So you have a cooler, and then typically we have if you see this, there is some droplets here. It's so it's not pure vapor anymore. So there are some droplets. So we need to separate the droplets. So in this case, we'll do this again. We'll have to separate them to protect the compressor in the next stage. Oh, I haven't. I don't know. I don't know what to name it. So it's just easier to just, use this. Put it there. Yeah, by default pressure drop is 0, and then the adiabatic. By default pressure is 0 and adiabatic. Yeah, you can change it what you want. So in this case, at least we are now separating the liquid from the vapor. So put the vapor over there, and then we put the liquid over here. So we liquid's only like 50 kilograms an hour, and then the vapor is 2 tons an hour. So now we can copy the whole setup. Copy the whole setup. Yeah. Okay. This one goes here. So we need to compress it from 350, not to this one, but to a higher pressure. For example, 50 bar, 60 bar, 6500 bar. 6500 bar seems to be okay. Right. So we compress it to 65 bar, and the temperature is 140 degrees C. So we cool it down still to 60 degrees C. So this is then second stage. This is then the second stage. And this is then the first stage separator. This is then second stage. Almost 12. So I'm thinking to stop this at this reactor. Yeah. So this is still at how much is this? 35 bar. This is 60 bar, 65. So I think we'll need another stage. So copy and then paste, and then yeah, put it here. This is third stage. 10 bar, 100. 100 bar. So we managed to get in the 100 bar. So we cool it down back. So in this case, we're not going to cool it down, right? So we just leave it as it is. So we're not going to cool it down because we need to have the 250 degrees C. Yeah, you need to have the 250 degrees C. So instead of a cooler, we will have to have the we're not going to use this. We're not going to use this. So we need to heat it up until 250 degrees C. This is then the methanol reactor. Reactor heater, yeah, whatever. This one, and then the out temperature is then 250 degrees C, and then delta P is 50 bar. So yeah, it's not that number, the 100 bar. So we can also increase this to 150 there. So you get at the end of the reactor is about 100 bar. So that's how we do that. Okay, so at the third stage, we are not cooling it down like in the other stages. We are now heating it up because we are not sending this to another compressor. We are sending this to a reactor. So now the reactor, since you have no so now Zahran, do you have any info on the yield and stuff, conversions? Otherwise, kinetics. If you don't, then in this case, it's to make it easy, just use the conversion reactor again. And because it's better that you have the kinetics, because this methanol synthesis, it is well known. Yeah, methanol synthesis is well known, so you can easily find the kinetics. You can easily find the kinetics, but if you don't have the kinetics with you, yeah, what can I say? You have to find it. But in this case, I'm not going to find. It's 12 o'clock already, so I'm not going to force you to find another kinetics. But say, for example, yeah, I will just do this for you. Conversion efficiency, yeah, it's not enough because this methanol you have to find, yeah, you guys have to find this because this is methanol synthesis is a well-known reaction, so you have to find it. Methanol synthesis from syngas kinetics. I'll show you how to get the kinetics, how to get the kinetics into the simulation, and then I think we can close for today, and then you can continue. Yeah, the same way that because I've been showing you how to get the information, which information to select from, and then so on and so forth. Kinetic modeling, see, kinetic modeling, solder, very easy. There's the methanol, so you can see this guy, kinetic modeling. You can find all kinds of stuff. Yeah. Just take one. Okay, not DME. I need to find just take this one. 100 bar. 100 bar. So we'll just use this one. Or the old one. Either of these three. So you can. I don't know what's taking so long. So while waiting, so we have these two reactions. So we need to know the kinetics of these two reactions. The methanol. See, the kinetics so complicated, so I don't think we're going to use this. I want to find something really simple enough, because this one you can also code that in Symmetry. I will show you how, but then because time is limited, I want to show you a simple one. Slurry reactor. Yeah, it's not slurry reactor, it's a fixed bed reactor. Nah, so it's not it. This seems to be more like it. Right, so we have these directions there, and then we have these directions there. This one we don't have it. Yeah, for the sake of this study. So now, blah blah blah. So complicated. This is so complicated. So we have K, 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 and then this K, sorry, K, and there's so many partial pressure of CO, partial pressure of hydrogen, and partial pressure of methanol, and then hydrogen. Okay, where are those Ks? Didn't show. Yeah, we need to find it. Anyhow, this one, this graph. Graph 8. They don't show how much these Ks are. Right. Okay, I don't have access to this. So I don't have access to this. So anyhow, simple kinetics. No, this one. I think you can access this, right, to your via UTP account. You can access this. For me, I cannot access this. Kinetic manual, kinetic manual.
So I think someone sent layer in the chat box.
Yeah, but in this case, I will show you. In this case, I need to know the because this is then K and then E. This is not fully kinetic. What are the kinetic is that it has to show the expressions of the contributions of the hydrogen and then the CO. Can you follow? It has to be we need to know the contributions of the CO and then hydrogen and then CO2. For example, like in this case, where is that stuff? Because what you show is the constants. Yeah, see, so in doing this simulation, getting the information correct is it already takes some days, which is much more important than simulating it. Okay. Say for example, yeah, if I'm showing you now here, what you put is then this K and then the K and then the Arrhenius activation energy. But I need to know the K on this is this then partial pressure and then this partial pressure of hydrogen and then the order. So all of these then the kinetic expressions, not merely not only this K and then E. Yeah, this K and E, it's only assumed that I don't know. Is this do they take into account the partial pressure of CO2 and then hydrogen, or CO2 only, or hydrogen only? And then what is then the order? Is it 1, 2, or 3? It is 1, 2, or 3. It's something that we don't know. Looking only at this table. Can you follow? So we don't know is this 2. Now in this case it is 2. But it could also be 1 or 3 depending on the catalytic system. So different catalytic systems, they will then require a different operating condition. They will then give us different rate expressions, because these rate expressions coming from the experimental value. Yeah, they do experiments using this catalyst, using these operating conditions, and then they get the data, and then this is then the fitted kinetic data. So I want to find at least a simple one that I can yeah, I can just use this here. But K equilibrium, I can use this one. This one is very much simpler. K equilibrium is how much then K equilibrium? Yeah. Results. This one. K equilibrium is this guy. Um, um, let's just use this here. See what happens here. I'll just use these equations to calculate the K equilibrium, and then put that equilibrium. For sure, you in the end you need to read this document. Yeah, you need to understand the information. But for the sake of this exercise, because it's already past 12, I'll yeah, I'll just use this K. No, I have another K. This K, I can get this one from that equations, and then this K is coming from yeah. Um, okay. Ah, oh yeah. This is there. This is it. Let's see the easiest one. I think this one, yeah. This one is the easiest one. So you can redo that letter with more complicated stuff, but that I will show you the easiest one so that you understand. So K, this K is this K, and then K0. So this K is a function of K0, and then this E and R. And then K equilibrium, we have the K equilibrium somewhere up there. Okay, so I will use this. I'll put it to the side. But this only for CO and hydrogen. Oh, yo, that means this only for this reaction here. It's only for this reactions only. So you need to find another one for this one as well. Okay, so for the sake of this exercise, I will just model for you this one and show you how to use this information, and then later on you can expand this. Yeah, later on you can expand this, and you have to expand this. I'll put this aside. Open another one. Oh, this is the one that I seen, I guess. Yeah. We have seen this. So we will use this. Okay. Goes to the where's my reactor? Plug flow reactor, because we have the kinetics. Um, this one, and then this methanol reactor. Um, yeah, and then this then okay. Now, since we only have like one kinetics, we only know one kinetics, so we will only use the first one, CO plus the first one, yeah, the first one, this one. You need to find the other one. copy add base component is I don't know, CO. CO is -1, hydrogen -2, or methanol is 1. Methanol is 1. Okay. Okay. And then kinetics. Now, kinetics. Just use this for the sake of this exercise. You need to find a better one, maybe, or simple one. Okay. Now, so we have E, molar concentration. So reaction kinetics. So in this reaction kinetics, the okay. So the default here is you have to the forward reactions E, and then there is also the reversible reactions over here. So this is then the forward kinetic, and then it's reversible kinetics. So here in this case, because we specify it to be molar concentration, then that means this then the everything is then the molar concentrations of this guy. Okay. In this case, so reaction order. Yeah. So in this case, you have like CO is then 1, hydrogen is 2, and then this is then methanol is then the -1, and then there's hydrogen as well, divided by this is also 1. So this expression is not the simple expressions that we get over here. Okay. So I think this is more this partial pressure, I guess. Yeah. So let me see. See, this is then a partial pressure. So that means we have to hey, what is that stuff? So we have to do advanced kinetic. And then this one is molar concentrations. This is partial pressure. It's in kilopascal. Yeah, I don't know. This is kilopascal, and then advanced kinetic. I think so. In this advanced kinetic, you can edit them, yeah. See partial pressure, and it's automatically edit, and then this we don't have any reverse reactions in this case. So in this case, you can just put this 0. This is also 0. Yeah. So everything here will be 0, and then the reactions is then the in this case we have K. Oh, A is then the A. So this A is then this K. A0 is then this one. So the unit is be careful on the unit, yeah. So in this case, just for the sake of keying the information. So 1.51 E minus 3, and then this is then kilojoule per kilomole. Again, this is an E, and then what we have here is then E divided by R, and then R is then 8.314. So so you have to multiply this to 8.3, 3,000 divided multiplied by 8, it's about 24,000, roughly. And then we make the methane, and then we make this. So we have K. So this information is then going to be put in this K. A is then this one, and then E is then this one, and so on and so forth. So we have K. It's complicated now already, yeah. So how do you call it? It's better that you use the simple one. But since you don't have it, yeah, it's your fault. So okay, yeah, that K is this K multiplied by partial pressure of CO. CO is P3. So P3 to the power of, no, not to the power, it's only one. And then hydrogen is P4, 2, right? And then minus partial of methanol, P6, divided by, that's the K equilibrium. So this K equilibrium is, where is that stuff? This one. So equilibrium is then exponent divided by exponents. I don't know if exponent is there, but we'll see. Exponent minus 9762 plus 11815 divided by temperature in Kelvin. Yeah, and then close. And then divided by, the whole thing is divided by this, open and then close and then close again, and divided by the P hydrogen P4. Yeah, so that should be okay, yeah. Notes, and then okay, yeah. Okay, so these are the equations. We'll see what happens, yeah. Because this is also my first time having quite complicated, not quite complicated, but okay, so we have now this, and then it says missing length, so we need to know what the size of the reactor. So there's, I don't know, maybe 5 meters or something, and then diameter is I don't know. We have 132 meter cubic an hour. So if we allow for 1 meter per second of velocity, and then you can calculate easily what is then the inner diameter. But in our case, just pick I don't know, maybe 5 centimeters. And then we have this like adiabatic reactor, yeah. Out Q is then 0. Yeah, it's not updating anything. Oh, delta P. Delta P is then the 50 kilopascal. There. So we specify the delta P. We say it is adiabatic. Yeah, we say it is adiabatic. So you can also do the same situation if you want to have it in isothermic or in adiabatic. You can do the same. Yeah, I've explained to you before. And then this exothermic reaction. So its temperature goes up, and then we can see the reactions automatically filled in. We have the kinetics, and then what is profile plot. You can also put a plot. Why is then mole flow? So yeah, which mole flow? Anyhow, so you can see mole fractions, mole fractions. Mole flow. So methane is constant because it's not reacting. Water is also not reacting. We are going to make methanol. So methanol is then produced, and then CO2. CO2 is not doing anything because we only use the first reactions here: methanol, CO, and hydrogen. So these three components, they should change. So methanol we see is changing, is being produced. CO is reduced, and then hydrogen is also reduced. So that's how now I'm showing you how I've shown you now how to apply. Where's that stuff? How to apply kinetics you get from your experiments or from others' experiments, this kind of kinetics, and then getting this number. I don't know if this number is correct. Yeah, you have to find it. It seems to, well, it works, but then the numbers may not be correct. So depending on the units that we are getting from any papers or from any source of information, so we need to be able to make sure that we get the correct number. yeah, the correct unit. Okay, get the correct unit done, and then and now in this one is coincidentally we get, it seems to be logical, the results. It's not that very so you can also see we still have some carbon monoxide, so if you reduce it to 2.5, for example, uh, um, see 2.5, see how much that was that, I don't remember. Snipping. This is then the results for 2.5. You could also do a sensitivity analysis, yeah, like a case study. So if I put this 2.5 and then I put this 5, and then I compare it. So at 5 meters, sorry. So at 5 meters, there's nothing happens basically. I mean, at 2.5 meters, everything is already. This then basically maybe the end result. So if I increase the reactor much further, that means I increase the residence times. It doesn't do anything yet. So what we could do as well, we could also increase the temperature. For example, 260 degrees C. See what happens. We see methanol 39.52, and then enter 39 point. How much was that? 52 to the 9.52, and then you increase the temperature, and then it drops. Yeah, it's something that you can play around. Yeah, something that you can play around. So 250 is that the original one. So something that you can play around. So I think I've shown you quite a number of things on how to use symmetry, at least the basic one, up until the selection of reactor, the how we can input the advanced kinetics into the system. Then make sure you always in this kinetics, make sure that you get the units correct. Yeah? Make sure you get the units correct. This one may not be correct entirely, but so for your exercise, I think instead of using this, you could also use this. Yeah? You could also search for more, find in textbook on what the kinetics of the methanol synthesis are, because then you can learn a lot. Yeah. So I've been asking you right from I'm saying to you right from the beginning that you have to be able to answer all of my questions. So all of these questions that I asked you, these are all information required to make the simulation correct, to make the model of this plant correct. Yeah, because once we get this model correct, and then we can then have it. I mean, the result will be then be more representative. I think I have to stop at 12:30. Do you have any questions so far? So, or is this clear or not very much clear? Hello. You could get this temperature into the process calculator. Yeah. So you have all informations in here. Hello, hello, hello. Are you guys all gone already? Hello. I can only imagine how frustrating your lecturer would be, teaching you online class. um,
There's you're laggy.
huh?
Can I hear?
Say it again, Zahran, because your voice is breaking up, and then hello, hello.
I don't know. I think I cannot hear you clearly.
You cannot hear me clearly.
For me lah, for me.
And then why did you not say so right from the beginning? Because right from the beginning, I asked already, can you hear me clearly? And some of you said yes. And then
No, yes. Just now is yes, but I cannot hear what you're trying to ask just now.
so I was trying to ask this now is that can you follow this? That's number one. Do you understand what I've been doing? That's number two. And then can you work it out further for your, because now up until now I think we are here. We are here. Yeah. We haven't get to this part of recycle, but I think we can. I don't know. We can have another session later on. Yeah. But in this case, up until here, can you then move forward? We will try. Yeah, very good. If not, then let me know. Again, I'm not really sure how much you can gain in half an hour or even 1 or 2 days. But nonetheless, I've showed you where to look for the information here in Symmetry. You can find in the simulations over here in this help file, and then I've shared with Shahira and Winnie on this part, which you can then follow. I think the kinetics is here. See, distillation column is there. It is, I think you will need to use this later on, flash vessel distillation columns. And then the plug flow using kinetics is also there, so you can redo this and then use the different one. The rest is, what else? I've showed you how to use controller. I've showed you how to use a case study. But for optimizer, maybe it's a later occasion. Do you have any questions? So if you don't have any questions, then what can I say? Any questions? Do you understand this? Do you understand? How much do you understand? Well, very difficult questions. Okay. Anyhow, um, have you tried? What matters in this modeling and simulation is not the tools. Yeah, what matters is that your logic on the process. Yeah, your understanding on the process. That is what matters. It's not about the tools. It's not about this symmetry or HYSYS or aspect pass or proto or whatnot. So your understanding on the process is what matters. I think I've been asking you many times already what to do, what are the operating conditions. If you don't have all of this information, nobody will be able to help you. Okay? Okay or no? Uh, um, how many people are alive now until now? I think I know Zahran is alive, Nur Hidayah is alive as well. The rest, I don't know. Um, okay, do we have our moderator or the MC for this? Or they are all gone as well? I don't know. If they are all gone, and then I can just close the session. I see Nur Shahira. Is this the MC? There are so many Nur Shahira here. I cannot recall. Organizer here. Hello. Shahira. Oh, she's not here. Yeah, well, even the organizer is not here. So, so shall we close this, Zahran? Do you have any other questions? Hello. No?
No from me, sir.
Okay.
No, sir.
Okay. So, okay, Ezra is alive as well. So if there is no question, so and there is no MC as well, so we'll just close ourselves for today's session. Yeah, I think I wish you lots of success. Let me know if you need any more help, or you can also discuss this with Dr. Hadi on how to use symmetry. And then if you need further on continuing this, we can think we can do another session in the future. Or if you want to have like this dynamic simulation as well, you can always contact me. No problem. So what I need you to do is to read a lot. Yeah, there's nothing else. There's nobody or nothing can help you. to solve any problem if you don't read a lot, if you don't talk to people who know better a lot. Yeah, so keep on learning, and then I wish you lots of success in the future. Okay, so thank you. With this, I think I will excuse myself. Yeah, bye bye, bye bye.
Wait, sir. Wait, sir.